Okay, so this morning we start with Robert Young, and we have the usual 90 minutes.
Thanks. So previously we've been talking a lot about functions. Today I want to go from functions to sets. I want to talk about rectifiability and what's called uniform rectifiability. So rectifiability a rectifiable set is a sort of analytic analog, a geometric measure theory analog of a surface. A k-dimensional rectifiable set is kind of like a k-dimensional surface. And we can define, there are many ways to define rectifiability, but there are two that I think are most common. You can define rectifiability in terms of parameterizations, and you can define rectifiability in terms of differentiability. So in terms of parameterizations, so we say that a set E, let's say set in Rm is K rectifiable if there exists countably many Lipschitz maps, countably many FIs from R, it's k-dimensional, so Rk to Rm, Lipschitz, such that the set is covered by these maps up to something of measure 0. So E minus the images, minus the union of the images of these maps, Rk, has Hausdorff measure 0. Right? And there are lots of examples of rectifiable sets. Like I said, any k-dimensional surface is a rectifiable set. So, for instance, one rectifiable set, you have lines, you have curves, you have circles, you have graphs in the graph theoretic sense. You can have a lot of different, anything you can draw with chalk is a rectifiable set, pretty much. And so the question, though, or one issue, though, is that it is not immediately obvious what sets are not rectifiable. Certainly, you need that you can have, so you need the Hausdorff dimension of your set to be, what do I want to say? The Hausdorff dimension of your set has to be let me, I guess, certainly if E is K rectifiable, then the Hausdorff dimension has to be less than or equal to K. But, there are lots of sets with Hausdorff dimension 1, say. Which ones of those are 1 rectifiable? And so, for example, you can take the 4 corners Cantor set. So the 4 corners Cantor set is the set that you get by taking, let's call this K0 is a 1 by 1 square, is a unit square, or the boundary of a unit square. K1 is going to be what you get if you take that unit square and you take 4 squares at the 4 corners of the square. So we cut out 4 corners of the square, which are 1/4 by 1/4, and these are still contained inside the unit square. And similarly, K2, we take 16, same thing with each of those 4 squares. You replace each of those 4 squares with 4 smaller squares. These now have these are now 1/16 on a side, and these are still contained in the unit square. This is K2. And then we can take the limit of these sets to get what's called the four corners Cantor set. I'm not going to try to draw it. Right. And so each of these, you can check that each of these, this is made up of, in general, Ki consists of, what is it, 4 to the I squares of side length I, or sorry, 1 over 4 to the I. And so K infinity, the limit of these can be covered by exactly those squares, exactly those 4 to the I squares of side 1 over 4 to the I, which means that the Hausdorff dimension, the Hausdorff 1 measure, the Hausdorff 1 measure of K infinity is finite. And likewise, you can check that the Hausdorff measure is positive. So this is a set of Hausdorff dimension 1. Is it rectifiable? Can we cover it by countably many Lipschitz maps? No, it turns out we can't. This is what's called purely unrectifiable. And that means that for any Lipschitz from R to R2, Lipschitz, the image of F intersect this set has Hausdorff measure 0. You can't cover any of this set, or you can't cover any positive measure portion of this set by a Lipschitz curve, right? So how can we prove things like this? How can we tell that this is not a how can we tell that this is not a rectifiable set? Well, like I said, another very common way to define rectifiability is in terms of differentiability, in terms of the infinitesimal structure of the set ability. So it's a theorem that if sigma is, I believe you need this to be Borel. And then if we define for all x in R, and so this is a subset of Rm, for all x in Rm, for all R greater than 0, we're going to let sigma sub x comma R, this is the rescaling of sigma around x by a factor of R. So to write it very crudely, we could write sigma translate by x and then rescale by a factor of R. If we want to write it out, this is the set of points of the form y minus x over R, where y is a point in E. Right, so what this does is this takes sigma, you take a point x, you move that point to the origin, and you blow up the ball of radius r around x to the unit ball. Then sigma is rectifiable, let's say k rectifiable, if and only if the restriction of the Hausdorff measure, if and only if the Hausdorff measure restricted to sigma xr, what this is the yeah. So remember, this is the set that you get by rescaling sigma around x. If these measures converge weakly to the Hausdorff measure, sorry, I need a little more space for this. So then sigma is k rectifiable if and only if for almost every x in sigma, if you take the Hausdorff measure, there exists a plane Vx in Rm, a k-plane, such that if you take the Hausdorff measure restricted to sigma xr, this is a sequence of blowups of sigma, then these converge weakly to the Hausdorff measure restricted to the plane. And so we call these planes Vx, the approximate tangent plane of sigma. Right. So this is a sort of differentiability criterion in the sense that it describes what these sets look like on the infinitesimal scales. Sorry? With respect to, yeah, almost every HK, almost every. Yeah. So this is a differentiability criterion in the sense that it deals with the infinitesimal structure of the set. It says that at almost every point, your set is infinitesimally a plane. That in an appropriate sense, your set blow-ups of your set converge to planes. And so, in particular, this is one way of showing that the four corners Cantor set, and indeed any positive measure subset of the four corners Cantor set, is not rectifiable because you can take blow-ups of the four corners Cantor set, and all you get is more Cantor sets. You never get something that converges to a plane. Is this okay so far? And so what this theorem does is it gives us a deep connection between, this connects this definition based on parameterizability, and differentiability. That you can only have this linear, that if a set has this linear infinitesimal structure, then it's parameterizable by Lipschitz maps. And conversely, if a set is parameterizable by Lipschitz maps, then it has this infinitesimal affine structure. And so, you know, just like before, this is a qualitative condition, right? Both these conditions are just yes or no. The set either satisfies the criterion or it doesn't. And so, you know, we can ask, how can we quantify this? How can we quantify these notions? And really, how can we measure this sort of parameterizability or this sort of differentiability in a scale invariant way? Because everything we've been talking about this week is scale invariant. Okay? So that's what I want to do today. I want to talk about how to measure parameterizability and differentiability of sets, how to measure rectifiability of sets in a scale invariant way. Is this okay so far? Any questions about anything so far? Okay. So let's take this one definition at a time. Let's start with the differentiability. Let's start with the differentiability definition. So what do we have here? So this says that for a rectifiable set, if you zoom in at any point, then on an infinitesimal scale or at almost any point, your set is infinitesimally close to a plane, or your set can be infinitesimally approximated by a plane. And there are really two things, well, there are more than that, but there are two big things that we can gather from this. The first one, so let me just copy the criterion because I'm going to erase that sooner or later. There are two things that I want to gather from this criterion. One is a density estimate. Because what does this say? This says that this set, that blow-ups of this set converge weakly to the ball, or sorry, to a plane. So in particular, this tells us that the measure, the Hausdorff measure of the unit ball intersect this blow-up converges to the Hausdorff measure of the unit ball intersect Vx. But Vx is just the plane, so it's just the so this can be any plane. This is just the volume of the unit k-dimensional ball. Or equivalently, because we know how Hausdorff measure scales with rescaling, this tells us that the Hausdorff measure of sigma intersect the ball of radius r around x converges as r goes to 0. Sorry, I guess I should say the limit as r goes to 0. Let's see, so we rescaled this, so this should be on the order of 1 over, this should be on the order of r to the k. So let's normalize that, and we get that this is the Hausdorff measure of the unit ball intersect the plane. So rectifiable sets should have strong density estimates. The density of the set should converge at almost every point, and it should converge to the same number at almost every point, just the volume of the k-dimensional ball. If we want to make that scale invariant, then that should apply not just to infinitesimally small balls, but really to all balls. But in that case, we can't ask for quite as strong an estimate because, if you have a set where every ball has volume c times r to the k, that's a very, very strong condition. And so let's ask for a weaker condition. This condition is called Alfor's regularity. We say that a set is Alfor's regular for c in, let's say, c greater than 0. A set sigma is c Alfor's regular, or sorry, I guess is let's say c k Alfor's regular. Actually, let me. Let's keep the notation simple. Let's keep the notation simple. Let's say this is k Alfor's regular if there exists a c greater than 0, such that the measure of the set intersect a ball of radius r is between c r to the k and c inverse r to the k for all x in sigma, and let's say for all r between 0 and the diameter of sigma. You'll see different versions of this. You'll see versions of this where you ask this to hold for all positive r, which means that you're applying this to sets with infinite measure because it has to apply to arbitrarily large balls as well. I'm going to stick with this. It makes things a little bit more complicated, but it lets us deal with bounded sets a little more easily. This condition is, it's a very useful condition. This is not enough to imply rectifiability. This is not enough to imply rectifiability, and the example is the four corners Cantor set. Okay so far? So this is one thing that we can draw from this criterion, is that since this converges to a set to a plane, that gives us a bound on the density. Another thing we can draw from this is flatness. Another thing we can draw from this is flatness. So if the Hausdorff measure restricted to the blowup of sigma converges to a plane, that means that there exists, what do I want to say? That means that for every epsilon greater than 0, let's say, so if this is satisfied, if these converge, then for every epsilon greater than 0, if let's say the epsilon neighborhood of Vx is the epsilon neighborhood of Vx, then this is also saying that if we take this blow up and we intersect with the epsilon neighborhood and we intersect with the ball of radius 1, then the measure of this if sigma xr is exactly the plane, oops, sorry, I should say, sorry, I want this to go to 0, so let's swap this around. So I want to intersect with the ball of radius 1, and then I want to subtract this neighborhood. So if this were exactly the plane, if this intersection were exactly in the plane, then this would be the empty set. We can't quite say that this is the empty set because we only have weak convergence. The best we can say is that this goes to 0. That at small scales, our set is closer and closer to the plane. For most points in the set are closer and closer to the plane. And so how can we quantify this? Well, one thing we can do is the following. So for every x in sigma, for all r greater than 0, we're going to let, and for all p from 1 to infinity, we're going to define beta, what's my notation? Yeah, and p a k-plane, we're going to let beta sub sigma p of x r with respect to p. Sorry, the notation is a little complicated. We'll simplify this notation in a little bit, but what this is going to measure is how close sigma is to the plane p in the ball of radius r around x, measured according to the LP norm. So this is going to be the integral. Shoot, have I gotten this right? I think I need to do that. Okay. This is going to be 1 over r to the k times the integral over sigma intersect the ball of radius r around x of the distance from y to p over r raised to the power p integrated with respect to y And then this is an LP norm, so I'm going to need to take the, okay, so what is this so far? This is taking the distance from points in the set to the plane, normalized by r because we're in the ball of radius r, raised to the pth power. We're taking the average of those pth powers over this intersection because assuming that our set is Alforth regular, this intersection has measure on order r to the k. So this is basically the average pth power of the distance between a point in the set and this particular plane. And so if we want an LP norm, we should take the pth root of this. And so this is this is beta sigma p. This is a way of measuring how LP close sigma is to p on the ball of radius r around x. Right? Here, we don't want to fix a particular plane. We want to let the planes vary. And so we'll define the minimum of these, beta sigma p. If we drop the p from the notation, this is the minimum over p of beta sigma p xr. Right? So this is basically a way of measuring how close the set is to any plane on the ball of radius r around x. Okay? This is, and previously, the past couple lectures, we were talking about epsilon differentiability, which is, if you have a function, can you find an affine function which approximates that function up to an error epsilon? That's essentially the L infinity version. Epsilon differentiability is sort of the L infinity version of this. Because but to deal with sets properly, we can't do an L infinity approximation because there may still be some points outside the epsilon neighborhood of the tangent plane. This is just going to give us a bound on how many points can be how far from the tangent plane. So yeah, sorry, where? Oh, that's supposed to be there, right? That's supposed to be a sigma, by the way. Sorry. So this is this is a scale invariant way. So beta sigma p is a scale invariant measure of the flatness of sigma. We really want a we really want a yeah, we really want sorry, this tells us about the set at a particular point or at a particular scale. We really want a criterion that takes into account all points and all scales because we're looking for some sort of scale invariant criterion. And we can take inspiration from what we did with the with Carlson sets and quantitative differentiability. We could ask, for instance, that we could ask, for instance, that the set of x and r, where this is bigger than epsilon, we could ask that that's a Carlson set in an appropriate way. That would be called the weak geometric lemma. We're going to ask for something a little bit stronger. We're going to ask for something called the strong geometric lemma. And the strong geometric lemma is based on a theorem of Dorn-Soro. I guess it's based on a theorem of Doran-Soro and also on also on some work of Jones. I guess let me say of Doran-Soro and Jones. But the version that I'm going to use is most directly from a theorem of Doran-Soro about harmonic analysis. Um, so Doran-Soro's original theorem was stated in a much more broad, in a broader way for Sobolev functions. I'm going to state a simpler version for just Lipschitz functions and graphs of Lipschitz functions. So let's let f from R k to R m minus k a Lipschitz function. And let's let gamma f be its graph. Then Doran-Soro showed that what do I want to say? So Doran-Soro showed that if we take the following double integral, let's see, for any p between 1 and 2, any y in the graph, and any r greater than 0, let's make that a capital R, let's make that a capital R. Capital R greater than 0, the integral from 0 to capital R of the integral over the ball of radius r around y intersect the graph of the beta number of the graph with respect to p x comma r integrated appropriately. So we're going to put the Hausdorff measure on the ball. We're going to put the Hausdorff measure on the graph, and we're going to integrate with respect to dr over r. And I need to square this. That this is less than some constant. What do I want to say? So let's say so this is less than some constant times the size of the ball. But we know what a Lipschitz graph looks like. We know the size of a ball in a Lipschitz graph. This is bounded by some constant times r to the k. Right? So by now, hopefully, you've seen enough integrals like this to have an idea of what we're saying. So again, yeah. No, for all of these. This is like the Carlson condition. We want a condition that holds on every ball. Yeah, for all p, for all y, for all r. Yeah. So this is very much like the Carlson condition. This bounds a particular quantity on every ball centered on the graph. And so what is that quantity? Well, we can think about, so we're saying that this is bounded by the size of this intersection. So another way we can think about this is that this says that, we apply Fubini. Another way of saying this is that the average of another way of saying this is that the average of the integral of beta square the average of the integral of beta square, sorry, is less than or equal to some constant. Is less than or equal to some constant, depending on, well, actually just some universal constant. And so this is saying that this is saying that the average of this on the ball is bounded. And what is this? This is a scale invariant way of measuring the curvature of gamma on all these different balls around X. This is we're integrating the sort of the curvature of gamma at all scales from 0 up to capital R. Okay? Yeah? Yeah, well, so it should so if yeah so this is roughly the same as summing over all dyadic scales, because you can show where's beta. So we define this for a particular ball, but if you double the radius of the ball, or if you have the radius of the ball, then beta can't change too much. And so we could replace this with a discrete sum. We could replace this with a sum over all the scales of where R is 2 to the I. Is this okay? So this is the strong geometric lemma. This implies the weak geometric lemma in the sense that, well, in order for this to be finite, that means that the set of X and R where this is greater than epsilon has to be finite measure with respect to this integral, with respect to Hausdorff measure across dr over R. So this implies the weak geometric lemma, but it also tells you how fast the size of those sets decays. It's stronger than the weak geometric lemma because it gives you explicit estimates. Is this okay so far? And it's easy enough, So we'll go over this a little bit more. We'll see some more. We'll see some examples of this later because you can, I want to apply this to rectifiable sets. But even the way it's stated, you can try this for different Lipschitz functions, so you can try you can see how this integral works for, say, the absolute value function, or f of x equals sine x, or any of the other examples we've looked at. So yeah. Yeah, you want it to be, so you want it to be scale invariant. So you want it to apply to every ball. Well, because but how do you know how do you know what R is big enough? I mean, because we're defining this on a Lipschitz function, or the graph of a Lipschitz function, and the function is defined on all of RK. So we want to be able to account for, phenomena that happen at very big scales. The only concession, the concession that we make is the same concession that we made for the Carlson condition and the weak geometric lemma, which is that we say that the average of this integral on any ball of radius R is bounded, but this integral only takes into account the scales up to capital R, up to the scale of the ball that you're averaging over. So if I have a ball of radius 10,000, so if I want to study, scale 10,000, then I need to be looking at the average over balls of radius 10,000. Does that make sense? Yeah. Oh, because this is scale invariant, right? So this beta, do I still have the definition of beta? Yeah. So if you look at the definition of beta, right? If your set is Alforth regular, then the measure of this is order R to the K. And the distance from Y to P, because we're inside the ball of radius R, this distance is somewhere between 0 and R. And so we normalize, this is between 0 and 1. We take the pth power, this is between 0 and 1. We integrate. we integrate over a domain of size r to the k, and then we normalize by r to the k. So this is still bounded by a constant. We take the pth root. So so if your set is Alforth regular, this is always bounded by a constant, and this is scale invariant. And so this doesn't depend on scale in that sense. This is scale invariant in the sense that if we blow up our graph by a factor of 10 and we change all our radii by a factor of 10, we still get the same integral. Yeah? We really want, so if I remember correctly, so the original version of this was for Sobolev functions. So in the original version of this, in Doran-Sora's original version of this, it's a for so there are various other parameters you can vary in some of there are various other parameters you can vary, but what it ends up saying is that this double integral is less than or equal to I believe the 1-2 norm of f on the ball. And so the functions that where the exponent becomes a real problem, if I remember correctly, the functions where the exponent becomes a real problem are if you have domain with dimension bigger than 2, and then say take something which is completely flat, completely zero, except maybe it's got a little peak right in the center like that. And then you have to worry about exactly how you measure. Okay, if I take this ball, exactly how flat is this graph on this ball, and that can depend on the choice of p, right? So in practice, well, as usual, the only p's that the p's that people mostly care about are 1, 2, and infinity. But so I believe for everything I'm going to do today, you can essentially take p equals 2. But it does matter, but it doesn't. But you're pretty safe taking p equals 2. Yeah. Well, I think so. I can't remember off of the top of my head. So like I said, I know there are. If I remember correctly, there are problems that show up in where the domain has dimension bigger than 1. Um, the so I was using L infinity in the first 2 lectures just for simplicity and because it doesn't affect the results. What? Yeah, and so I don't. Sorry, I don't remember all the details of these theorems off the top of my head. I have to look them up when I use them. But you might be able to get away with this with p equals infinity if your domain is one-dimensional, but I can't guarantee that. What you have, but yeah, so I don't know off the top of my head if the strong geometric lemma hold. Well, I'm pretty sure that this does not hold for p equals infinity. Yeah. The exponent 2 is very important because yeah. So the exponent 2, we can like we have some flexibility about how exactly we measure flatness. But the idea, part of the reason that the exponent 2 is important here is orthogonality, is Littlewood Paley and things like that, because it's easy to construct like we could do, it's easy to construct examples which have a certain amount of where no matter how you measure flatness, you're going to get about the same answer. Like if I take sine f of x equals sine x, right? So if I take a ball of radius r, it doesn't matter whether I measure flatness L1, L2, L infinity. I should get the same answer, that this is about, distance 1 away from the plane. Whether you measure that distance L1, L2, and L infinity, it's about distance 1 from the plane. And so where this exponent 2 comes from is essentially the same Pythagorean theorem arguments that we made in the first 2 lectures. That if I take f of x equals sine x, I get one thing, but if I take, let's say I want to take the sum of epsilon times sine, let's see, how do I want to do this? Epsilon rho to the I sine of x over rho to the I. Right, and let's say I do this from I equals 1 to k, right? Then what does this look like? So let's take rho equals, say, 10. Then what does this look like? Let's say it's from 0 to k minus 1. What does this look like? Well, this is the sum of f of x equals sine x. And then we rescale. Let's flip the exponent. Say this is 1/10. And then we rescale. So this is sine x plus 1/10 sine 10x plus 1/100th sine 100x, and so on and so forth. All multiplied by epsilon because I don't want the Lipschitz constant to blow up too much. And then we can ask, okay, then what do the beta numbers look like? Well, if I take a big ball, then I'm just seeing this biggest scale, and so the beta number should be governed by this biggest scale. So if I take beta of, if I take beta of y comma, 5, this should be on the order of 1/5. But then if I look at a smaller scale, say scale 1/2, I don't really see the big sine wave anymore. I mostly see this second term in the sum. Again, so beta of y comma 0.5 is going to be again about the same. And likewise, every time I do this, I'm going to pick up the same, actually, and times epsilon. Every time I do this, I'm going to pick up about the same quantity. So every time I do this, so this is 5 times rho to the I. All of these are all going to be on the order of epsilon over 5. But what happens to the length of the curve? Well, the length of the graph, every time we apply this perturbation, every time we perturb by this epsilon scaled sine wave, is like 1 plus epsilon squared to the power of how many times we do this is k times, is about 1 plus k epsilon squared. So this is where that exponent 2 comes from. It comes from orthogonality. It comes from the Pythagorean theorem. It comes from functions like this, which have epsilon scale bumps at k different scales. And so the exponent 2. Shoot, did I erase? No. Okay. So the exponent 2. That's a property of Euclidean space. The exponent p is just a subtlety about exactly how we compare, like, a function like this to a function like this. Okay. Sorry, I do want, yeah, you know, it's an important, yeah, I'm willing to take as many questions as people have here because it's an important definition. So are there more questions? So then we say that sigma satisfies the strong geometric lemma if, and let me just fix a beta, let's fix p equals 2. If sigma is L-force regular, remember this means that its density is bounded above and below on any ball, and if this integral and if this integral y and sigma are between 0 and diameter of sigma, this integral beta, let's say L2 beta of x r squared dx Hausdorff measure on x, dr over r. If this is less than or equal to a constant times r to the k. In this case, we say that sigma satisfies the strong geometric lemma. It's L-force regular, and it has this condition on its curvature. It's okay? In particular, Doron-Soros theorem tells us that Lipschitz graphs satisfy the strong geometric lemma. So that's two conditions. The density condition gives rise to the strong geometric lemma. The density condition gives rise to L-force regularity. The flatness condition gives rise to the strong geometric lemma. So that's one definition of rectifiability. The other definition of rectifiability we have is based on parameterizability, right? A set is k-rectifiable if it can be covered by countably many Lipschitz maps from Rk. How can we measure parameterizability? How can we measure how parameterizable a set is, preferably in a scale invariant way? Well, one thing we can do is the following. We can define what's called the big pieces condition. We say that, let's say that sigma is L-force regular. We say that sigma has big pieces of Lipschitz images, B, P, L, I, if for every y in sigma, every r, let's say every x in sigma, every r between 0 and the diameter of sigma, there exists a map, if there exists a c greater than 0, such that for all x and all r, there exists a function from the ball of radius r around the ball of radius r in Rk to Rm, such that the Lipschitz constant of f is at most c, and f covers a reasonable fraction of the ball, which is to say that the measure of the amount of sigma that's covered by f, so sigma intersect the ball of radius r around x, intersect the image of f, that should be greater than or equal to C inverse times the measure of sigma intersect the ball. But because sigma is Alforth regular, we may as well say that this is at least C inverse times R to the K. So the reason that this is called big pieces of Lipschitz images is because that's kind of what it is. So the reason this is called big pieces of Lipschitz images is because it tells us that we have some set, so that for any point in that set and any ball around that point, we can cover not necessarily the whole set. There could be other stuff going on in the set, but we can cover 10% or 1% or 0.1% of the intersection of the set with the ball by a Lipschitz map which isn't too big. It's a Lipschitz map from the ball of radius r that has Lipschitz constant at most c. Right? So originally, the definition of rectifiability says that your set can be covered by countably many Lipschitz maps, where each Lipschitz map is defined on the whole RK. That means that any individual piece of those domains might cover just a tiny fraction of your rectifiable set. Here we're asking that we can cover our set by reasonably sized, reasonable Lipschitz constant maps that there's a piece of this intersection that I can cover by a Lipschitz map, which isn't too small, where there isn't too much other stuff going on inside that ball. Does that make sense? Like the sorts of things. Well, yeah. So let me. So I'll give some examples in just a sec, but I just want to say the conclusion. So first, is this definition clear? Because the reason I want this and this radius to be the same is because I want everything to be scale invariant. Like if I have a ball of radius 10,000, right? So if I have like a plane and an intersection with a ball of radius 10,000, then I can parameterize that by a one Lipschitz map from the ball of radius 10,000. Right, and so that's why I want the domain to grow with the size of the map, so that the Lipschitz constant can stay fixed. Oh yeah, you can absolutely do that. So I could do that, but that's the same as saying c square r over or c square Lipschitz constant there. Okay, so that's three definitions. So on the differentiability side, we broke this up into Alforth regularity. We broke this up into the strong geometric lemma. On the parameterizability side, we broke this up into, we can quantify this in terms of big pieces of Lipschitz images. Yeah? Yes, this is absolutely stronger than rectifiability. So on the differentiability side, we broke things up into a density bound and a flatness bound. On the parameterizability side, we gave this sort of quantitative notion of parameterizability. It is a remarkable theorem of David and Sem's that just like differentiability and parameterizability are equivalent definitions of rectifiability, these two notions are equivalent. If sigma is Alforth regular, K Alforth regular, then sigma satisfies the strong geometric lemma if and only if sigma has big pieces of Lipschitz images. In this case, we say sigma is uniformly rectifiable. And so this is, so this is stronger than rectifiability. There are sets that are rectifiable, but not uniformly rectifiable. But I would argue that that's not the most. I'll show you those sets eventually. But it's not the most enlightening way to think about this. So I would argue that the way you want to think about uniform rectifiability is this. This is a quantitative version of rectifiability. What does it mean? What would it look like to be for a set to be more rectifiable or less rectifiable? What spectrum does this define? Because certainly we can talk about sets that are obviously rectifiable. If I give you a square, right, this is obviously a rectifiable set, you know, it's a square. And you can check that this satisfies the strong geometric lemma. You can check that if I take, you know, a random point on the square, then the beta number of a ball around that point is going to depend on the radius of that ball. Like if I take a point that's close to a corner and I take a ball that's big enough to include the corner, then the beta number is on the order of 1. If I take a ball on the side of the square and I take a ball that doesn't include the corner, then the beta number is 0. And you can do this integral, the integral that shows up in the strong geometric lemma. You can show that that is going to be finite on the whole square. It's going to depend on, and it satisfies this bound on any ball. Likewise, it's easy to show that this has big pieces of Lipschitz images. Because, well, you know, if I take the whole square, I can cover that by one Lipschitz map with Lipschitz constant 4. If I take a piece of the square, you know, that's either an L shape or a line, and either way, I can parameterize the whole thing by one Lipschitz map with a small Lipschitz constant. So this has, you know, this quite easily has the strong geometric lemma. It only has a couple of corners, so the beta numbers are pretty small. And this obviously has big pieces of Lipschitz images because all the balls look very simple. What does the spectrum look like? How do we construct sets that are less and less rectifiable? How do we construct sets where these constants in the big pieces definition, where these constants in the strong geometric lemma get larger and larger? Well, one thing you can do is you can add more corners. For instance, so we don't want to make the set too big. Because we want to maintain Alforth regularity. We want to maintain a density bound. But what we can do is we can add more corners like so. So if I take 4 squares like this, as in the construction of the 4-corner set, where each of the squares is 1/4, and the whole thing is contained in the unit square, now my beta numbers are bigger. Because now it's not just if I take a big ball or a ball containing one of the original 4 corners, for those, I still get beta number bounded away from 0. But now also if I take one of these inner corners, if I take a ball around one of these inner corners, I also get a beta number of which is bounded away from 0. And so now, because now you have sort of 2 different scales where you can see that this is far from a plane. If I look at the whole scale, or if I look at one of these corners, both those scales, I can see that this is far from a plane. I can see this curvature, and they contribute to this integral of the beta numbers. Likewise, this is also harder to parameterize. Because, well, if I take small balls, sure, this is a corner. This is exactly the same as we saw over here. But if I take this whole circle, then now it takes a longer curve to cover the whole set. Now my Lipschitz constant goes up. Either my Lipschitz constant goes up, or I have to cover less of the set. And if we repeat this, this is just going to get this is going to get more and more complicated, less and less rectifiable, right? If I repeat this construction, so on and so forth, the nth stage in this construction still satisfies the strong geometric lemma for some bound. Like all these integrals are still finite because eventually you get to a point where it's flat. But this it has beta xr, bounded away from 0 at n different scales. And so this integral, there are going to be balls where this integral, and in particular, if I take the whole set, there are going to be balls where this integral is going to be on the order of n. Likewise, as we add more iterations here, it gets harder and harder to cover this by a Lipschitz curve, right? If I want to cover, the whole thing by a Lipschitz curve, that's a fairly long Lipschitz curve because that's to loop around all these little loopy bits. Even though the total length of those squares stays the same, it gets harder and harder to parameterize them. So this has big pieces of Lipschitz images, but C depends on n. Right? How do I know this has big pieces of Lipschitz images? Well, Kn consists of 4 to the n little tiny squares. It consists of 4 to the n squares of side length 1 over 4 to the n. So it's pretty easy to take, okay, I'm going to take C, I'm going to take C equals 4 to the n, and then I'm going to parameterize, in every ball I'm going to parameterize one of those little tiny squares. And that's enough. That's big pieces of Lipschitz images. So these are all uniformly rectifiable, but the constants are getting worse and worse and worse. Yeah. So C increases with n. Likewise here, this bound increases with n. In the limit, well, what this converges to, the four corners Cantor set. So you can draw one way of thinking about uniform rectifiability is that it gives you a way of sorting sets from this is more rectifiable to less rectifiable. And if we keep on making sets less and less and less rectifiable, we start getting to the point of sets that are purely unrectifiable. So there are sets that are rectifiable but not uniformly rectifiable. In fact, one example of such a set is this set here, where we take, here's the first stage of the construction, second stage, third stage, so on and so forth. If we just extend that out to infinity, that is Alforth regular, that is rectifiable because it's made of countably many squares, but it is not uniformly rectifiable because if you look at, the constants on this ball versus the constants on this ball, or this ball, or this ball, the constants are getting worse and worse. So there are sets that are rectifiable but not uniformly rectifiable, but also there are sequences of sets that get less and less rectifiable that you can measure that using this notion of uniform rectifiability. Okay? Any questions about this? Yeah. Sorry? Which for the big pieces? Yeah, well, I mean, so what does it mean? So what is the C in the so in the big pieces definition? What does the C mean? Oh shoot, I just erased it. I shouldn't have done that. Oh well. So we can cover a C inverse fraction of sigma intersect a ball by Lipschitz image of the ball of radius r, by a C Lipschitz image of the ball of radius r. So in the one-dimensional case, which is all these examples, all these Cantor sets are one-dimensional. In the one-dimensional case, we're saying that we can cover a positive fraction of the intersection of the set with a ball of radius r by a curve of length CR, right? And so let's fix R equals 1 and look at our Cantor sets, right? The density of our Cantor set stays the same. All of these Cantor sets have length 4. But if I want to cover, right, if I want to cover, say, 1/4 of one of these Cantor sets, it's easy in the first step. It's still kind of pretty easy in the second step. In the third step, well, now I have to go around this and go around this and go around this and go around this. So I'm still covering measure 1/4 of the set. But in order to do that, I need to add this line and this line and this line. And if I keep on going, it's just going to get worse and worse and worse, because now I have to cover, if I want to cover 1/4 of the set, then I have to cover, this little 1/16 and add in those little lines, and then jump over and do the same thing over here, and then jump over and do the same thing over here, and then jump over and do the same thing over here. I mean, the usual thing I recommend is, try to draw the Cantor set. Try to draw the 4/4 Cantor set. It's the same length. It takes longer to draw as you keep on going. And so that's that's one way of thinking about it. It gets harder to parameterize the Cantor set. Because it takes longer to draw the Cantor set. Okay? Yeah? Yeah. Yeah, yeah. Unlike, yeah. Yeah, so this is there are a couple of so back at the beginning of this series, I said, what are the reasons that we're interested in this sort of thing? And I said that one reason was this is stable under limits. Unlike ordinary rectifiability, this is the Cantor set. The construction of the Cantor set is a sequence of rectifiable sets that converges to an unrectifiable set. But if you have a sequence of sets with big pieces of Lipschitz images, then the Hausdorff limit is still going to have big pieces of Lipschitz images. Maybe you need something about like the semi-continuity of Hausdorff measure, so you make sure that the density doesn't go to 0, but if you can parameterize a positive fraction of each of the sets in the sequence, then you can take a limit of those parameterizations, pass through a subsequence, and cover a positive fraction of the limit. Or you can do the same. These beta numbers are well-behaved under taking limits. If this integral is bounded, then it should still be bounded in the limit. So this is stable under limits, which is one thing we wanted. This lets us deal with coarse geometry. If I take K100, the 100th step in the construction of the 4 corners Cantor set, this is rectifiable. It's made of 4 to the 100 little tiny squares. But if I take anything made of countably many line segments, that is rectifiable. But if I want to make a distinction between, well, the line is an arrangement of countably many line segments, and the K100 is an arrangement of countably many line segments. If I want to make a distinction between those two objects, rectifiability doesn't help me, but uniform rectifiability can, because you can say that one of these is rectifiable with the given constant and the other one is not, or is uniformly rectifiable with a given constant and the other one is not. And then the third thing that I wanted to, the third reason that I gave for why we're interested in this quantitative picture is that it gives us a way of looking at, it gives us a way to look at complex objects. Not in the, square rooted -1 sense, but in the sense of, well, in this sense, in the sense that the 100th layer of the construction of the Cantor set is a more complicated set than the line. It gives us a way of looking at complex objects, and it gives us ways to decompose complex objects into simpler ones. Um, Even though K100 is a very complicated set, you can break it up into a bunch of simpler pieces. You can write it as a sum, as a union of 4 to the 100 little tiny squares. And then and then you may be able to study the set by studying those little tiny squares. And so the reason there are lots of reasons to be interested in uniform rectifiability. There's a whole the origin of this theory, which I'm probably not going to get into, the reason people were interested in doing this was because they were interested in singular integrals and harmonic analysis. They were interested in questions about the Riesz transform, for instance. If you can define the Riesz transform for functions on an L-force regular set, and then you can ask which L-force regular sets is the Riesz transform a bounded operator? Which L-force regular sets is it not a bounded operator? And that has to do with these beta numbers because we know the Riesz transform is bounded on a plane. The real question is if we start perturbing that plane, what happens to the Riesz transform? It's going to depend on how much you perturb it by, and at how many different scales you perturb it by, and so you can express and so you can express all these things in terms of beta numbers, and you can use beta numbers to describe when the Riesz transform is a bounded operator or not, and this was really the origin of uniform rectifiability, was to study singular integral operators. So one reason to study uniform rectifiability is that I've given you two definitions of uniform rectifiability today in terms of the strong geometric lemma, in terms of big pieces of Lipschitz images, but there are another, half a dozen other definitions that are based on different properties, including the behavior of singular integral operators. And so it's a connection between all these different definitions. I'm probably not going to get into this because I'm not an expert on singular integrals, but I think what I'm planning to do tomorrow is to talk about this last condition, about how we can use notions of uniform rectifiability to try to describe complex objects in terms of sums and unions of simpler pieces. So, yeah. Exactly, yeah. Yeah. So I should mention that, yeah. And the SEL constants are bounded in terms of the BPLI constants and vice versa. Yeah. The quality of the bounds tends to be very, very bad, or at least what's known about the quality of the bounds tends to be very bad, because like the way that they prove these equivalences, the way that David and Sems prove these equivalences, these are two of the definitions of uniform rectifiability that David and Sems give. There are 5 others that they give, plus others that have been discovered since then. And a lot of the proofs of equivalence, kind of circle around the different definitions because you have to prove they're all equivalent. So the constants are very bad, but sometimes you just want there to exist a constant. Okay, I think I'm going to stop there.
Okay, are there questions?
So I have a couple of fast questions, I guess. Can you actually prove that, like, with by hand, that this four-corner counter set is purely rectifiable, like in this way, like saying the curves get too long and
Can you prove by hand that the four corners Cantor set is purely unrectifiable? I guess the proof that I'm aware of would be to use this rectifiability criterion to say that any positive measure subset has the wrong tangent cones.
yeah, or maybe you could also project on like two lines and
Yeah.
some.
Oh yeah, there's various versions involving like if you can find enough projections to lines that are measure zero, then it has to be purely unrectifiable. Yeah, things like that. I don't know. Yeah, I don't know. I don't know that many proofs that it's not that's purely unrectifiable.
Okay, thank you.
Yeah, so there are various subtleties in in these definitions. One of the notable ones is that I said big pieces of Lipschitz images. You know, you can define parameterizability for rectifiable sets in a lot of different ways. Like you can say it can be covered by countably many Lipschitz images. You can say it can be covered by countably many graphs of Lipschitz functions, and those are equivalent on the rectifiable side. But on the uniformly rectifiable side, it is a weird little subtlety that big pieces of Lipschitz graphs is not the same as big pieces of Lipschitz images. What makes it one thing that makes it a weird subtlety is that big pieces of Lipschitz graphs is equivalent to big pieces of Lipschitz images. Because basically every Lipschitz image has, well, yeah, sorry, I shouldn't say anything because I don't know the details. But yeah. But yeah, so that's a subtlety. I think projection. Yeah, and so what Antonio was saying was that another subtlety is that you can also define rectifiability in terms of having large projections in almost every direction. This does not quite work for uniform rectifiability because you know it's harder or maybe not known yet whether you can characterize uniform rectifiability in terms of projections. Yeah. So Antonio is saying that many large projections implies big pieces of Lipschitz graphs, but maybe not big pieces of Lipschitz images. Yeah.
So just to see if okay, just a check. Is a sine of 1/x not uniformly rectifiable?
Well, it fails to be L-force regular. The graph fails to be L-force regular because it's too dense near the origin.
Okay. Thank you.
Other questions? Okay. If not, we thank Robert again.
Okay, so today's lecture has this scary title, A Measure Theoretic Overhaul of Homotopic Spanning. And yeah, so maybe I don't have them here, so yeah, let's go. Interesting, so it doesn't, okay. So just to remind you very briefly what was the homotopic spanning, since it's like hour number 4 of homotopic spanning for you, so you should know by now. But we have this closed set W, and we consider the complement of W omega open. So W has the role of the wireframe that you want to use to observe a subfield. And there is this notion of what does it mean to span a wireframe that is based on considering a family C of embeddings of S1. So these are smooth injective maps from S1 into omega. And the property that we impose on this family C is that it is closed by homotopies relative to omega. So if gamma and gamma tilde, if gamma is a curve in the family and gamma tilde is homotopic to gamma relative to omega means that as you deform one curve into the other, you don't want to exit omega. That's what it means. So then also gamma tilde is in the family. So here there is an example where W consists of 4 closed disks in the plane. I am declaring 3 generators, gamma 1, gamma 2, and gamma 3, So gamma 1 wraps around one disk, gamma 2 wraps around one disk, gamma 3, here I've chosen a gamma 3 that wraps around two disks at one time. Okay, so the three are not homotopically equivalent. I cannot deform one into the other without crossing W. And then we say that a closed set S is C-spanning W if it intersects every curve gamma in the family. Here, of course, there is a little abuse of notation. I should write gamma of S1, the image of S1 through gamma intersects S, okay? I'm writing gamma intersects S because otherwise it's already a mess like this if I even try to be more precise. It's horrible. So there is one important thing here. So if you have not seen the previous lectures, for example, here you see if I don't input the Vincenzo, this one is for you. If you don't put gamma 3 in the family, okay, you just gamma 1 and gamma 2, the minimum of the length of S is going just to be these two segments, right? But since I declaring gamma 3 in my class, just two segments are not going to be spanning because they are not going to intersect gamma 3. And so I force the observation of this other thing. So the choice of C is actually our way to see different minimizers. I think this is a very interesting idea. More generally, again, I make these considerations because this is a school, okay? So I'm trying to be pedagogical in my presentation. I think it's very interesting that we have one energy that is Gauss capillarity energy, right? And then you're somehow exploring this energy landscape by imposing different conditions, right? So a kind of minimality allows you to observe regular objects with physical significance, and essentially by changing the kind of conditions you impose on the problem, you go and observe different things. I think this is really nice. And so a remark, however, is that this notion is quite how to say, it's quite delicate because it's unstable by modification of your set S. Pointwise modifications destroy it. So if you take 1 point away of S, then you lose the C-spanning property. And this doesn't prevent us to prove theorems. I mean, we have proved the existence for the Plateau problem with this formulation, and we have proved even the soap film capillarity theory with King and Stuvard. We have fought for 70 pages competitors and all sorts of variants of the idea of cup and competitors in the setting of wet films and so on and so forth to make it work. So it's not impossible to make it work, but it's definitely a huge pain each time to work with this condition. And it also means this kind of pointwise conditions is not very, it's completely incompatible with distributional compactness, which is also annoying. So there are several problems, okay, in working with this thing. So the question is there a usable equivalent notion of C-spanning which is stable by H-null modifications? So, and right now, the motivation that I am proposing for this is that is very philosophical. I would like to have something more robust, mathematically speaking. So on the basis of my experience, as a mathematician, I know different tools and I say, yeah, but this is a bit of a pain in the neck. So maybe there is a better way of formulating this. So this is not why in reality we ended up doing what you're going to see in a few slides and it's going to scare you for the rest of your life. So this is not the reason. The reason is that we did it because we really, really, really had to do it. And the original motivation of all this problem is not wet soap films. It's another story. We'll come at the end. Okay, so it's like for doing the original thing I wanted to do in 2016, eventually we had to do this thing. And then we do this measure theoretic overhaul of the homotopic spanning, we realized that we could do much better theorems on the wet soap film theory. So it's an incredible story of luck. So there is no big insight on my side. But it's even more luck because the solution to this problem, at least the solution we have found, relies on a completely esoteric definition that I invented with Cagnetti, Colombo, and De Filippis 12 years ago, studying symmetrization theory that is now here with us. So let me explain where these things come from, because it really comes a long way. So and the fact that I knew it because I did it essentially, I don't think many people has read these papers in details. So for me, it's an incredible coincidence. So what's the story here? Symmetrization theory, you have a function from Rn into the non-negatives, and you define f of v, it's called the Steiner symmetral defined by v. So essentially, you have in coordinates in Rn plus 1 zt with z in Rn. You take all the points zt with absolute value of t less than v over 2. So it's a symmetric set with respect to a hyperplane. And you say that a set of finite perimeter E is V distributed, or just a set, is V distributed, so is distributed by the function V, if you look at the slices of your set EZ, so maybe I should have written it on the slide. So what is this? Oh, there is no, yeah. So here, this E of Z is the real numbers T, such that Z comma T is in E. So it's a very standard notation. I think it's self-explanatory. So if the length of the vertical slices with respect to this hyperplane is given by the function V. So there will be many sets distributed by a given function V. So something that you have is that by Fubini theorem, the volume of every set distributed by V is the same as the volume of f of V, simply because all the slices have the same measure, right? The interesting inequality, the Steiner inequality, is that you are always decreasing the perimeter. So by passing from a set to f of v, to the Steiner symmetral, you decrease the perimeter of your set. The measure of the boundary of the set goes down. So this is a classical theorem in the calculus of variations, because that was introduced by Steiner in the proof of the isoperimetric inequality. Okay? So it's a very classical topic. And the problem we were interested in is the rigidity problem for the Steiner inequality, because obviously, if your set E is a vertical translation of the Steiner symmetral, so it's just a Steiner symmetral, but rather than being split by Rn, it's just translated up or down by some factor t, okay? So obviously it's an equality case. Now the question is, if a set is V distributed and has exactly the same perimeter as the Steiner symmetral, right? Is it true that your set E is itself a translation of the Steiner symmetral or not? So this question is interesting because when you use this theorem to prove the symmetry of minimizers in the problem that you want, say in the isoperimetric problem, you say, I have a minimizer with a volume constraint, so the symmetral has the same volume. I am decreasing the perimeter, but it was a minimizer, so I didn't decrease the perimeter. The perimeter stayed the same by the minimization. So if after the Steiner process, I still have the same perimeter and rigidity holds for the function that distributes my set, then my set was a translation of the symmetral in that direction, and therefore it had the symmetry. And then you can start playing with this argument inside the proof of the isoperimetric inequality. You know that there exists a minimizer, you symmetrize it with respect to this direction, and you get another minimizer, and then you do the orthogonal direction, and so on. You build on that, eventually you prove that every minimizer must be a ball. So you get the balls are minimizers, and they're the unique minimizers just in one shot, okay? So, but rigidity in general may fail, okay? So, and these are two examples in the plane of why rigidity may fail. So one possibility is that the function V has a jump on the set where it's positive, right? So if your function V has a jump, this is the graph of V. So you see I have a set E, this will be the symmetral, but they have the same perimeter because the length of these two vertical segments is the same as the length of the vertical segment that is. I'm just translating this thing up and down. I don't change the perimeter. So in this case, if the function that measures the length of the slices is jumping, I could violate rigidity. Another example is here. You see, the function v is 0. The function v is 0 in a lot of places, right? It is 0 here too. But there are some zeros of the function v that could be particularly annoying because they may be those that allow you just to do vertical translations, right? And then essentially it's like it's disconnected. So I mean, it's just two different pieces that are maybe are symmetric in themselves. But so this is just a plane. Eh? So, and then there is a theorem by Andrea Cianchi, Miroslav Schlebik, and Nicola Fusco that appeared on Annals of Mathematics 20 years ago, which essentially tells you that if you exclude these two mechanisms for destroying rigidity, then you have rigidity. So the theorem says, let's take V to be a BV function. Why a BV function? Because if you are a set of finite perimeter, your distribution function is going to be in BV. They assume that V positive is open and infinite volume. This is not really needed. They assume that this object here, V hat, is positive almost everywhere on V positive. So this V hat, don't worry too much about the definition. It doesn't play a big role in this discussion. Is what is called the approximate lower limit of U. It's essentially a sort of lower semi-continuous envelope, okay? But it has a super cool property. It has the property that every Lebesgue representative of V will have the same V hat at every point in Rn. So that's the key problem. So, because when you work with these measure theoretic objects, right, most quantities are just defined almost everywhere. So it's absolutely fundamental to, in order to get anywhere with finer questions, to have objects that are univocally defined at every point of the space in a meaningful way, of course, not just in an arbitrary way. So one way of doing that is introducing the upper and lower approximate limits of a function, of a measurable function. So this guy V with the hat like this is this sort of measure theoretic stable lower semi-continuous envelope of V. Okay? So in a sense, if this guy is positive, and this is the guy that maybe the upper limit will be positive and the lower limit will be 0. So you really need the lower limit to be positive everywhere, okay? Positive almost everywhere in the set where V is positive. Notice that the set where V is positive is only defined Lebesgue almost everywhere. I'm sorry, I'm insisting on the almost everywheres because they're going to play a role, okay? So it's important to start thinking in those terms. Okay, if this guy is positive, which means essentially something like this is excluded. I don't allow even one point like that, okay? And what is DSV? BV functions. So the distributional derivative is a Radon measure. There is the absolutely continuous part, and if it's only that, it's a W11 Sobolev function. And then there is the jump and Cantor part. So DSV is the parts where the function jumps and the parts where the function doesn't jump, but still has a Cantorian derivative that is not absolutely continuous with respect to Lebesgue. You want this guy to be concentrated away from V positive. So maybe V positive, then it jumps at the boundary of V positive. That's fine. That's a jump. It's fine because it doesn't matter. You don't, when you do this tiny symmetry, it's just lateral perimeter that you conserve. But you really want nothing like that happens inside. So if these two conditions holds, then rigidity holds for V. Okay? So, and then looking at this theorem, right, you see that it's very far from being a sharp, a necessary condition, let's say, right? So here you have two examples of polyhedra where, for example, here you see there is a jump. So here, this square is the projection of this set. The set where the jump is positive is a line through this set, right? So there is a ton of point. So the singular part of the measure inside V positive is definitely there. Still you have rigidity. Because you see, I cannot really start translating these two pieces because here I see 0. So as soon as I move the right piece up or down, I create some lateral perimeter and I increase in the Steiner inequality. Here there is another example where you see the set V equals 0 Here V is continuous, so there is no approximate upper and lower anything, okay? It's much simpler. It's polyhedra. So here the set V equals 0 is just a segment that intrudes inside V positive, but again, I cannot really move this thing because it has a sort of connectedness property, right? So if I try to move it up or down, I mean, I create perimeter. There is nothing I can do. That's rigid. So trivial examples of polyhedra shows you that you can't, you should be able to do much better than that, right? So what could be an example, looking at this, what could be an example that it's problematic? So here V equals 0 is rather innocuous because it doesn't disconnect V positive. So imagine that I continue my line all the way up to here. So instead of stopping being 0, I go on. Then again, it's the example I showed you before. I can move it up and down and violate rigidity. So in general, I could imagine situations where V equals 0, and then maybe here I have another line where V is jumping as a positive jump. And then combining a bit of V equals 0 and a bit of positive jump, I create a set that disconnects V positive and then gives me the ability of translating the two pieces. So there is clearly a theorem like that to be proved. So the idea of a theorem would be this. Say that you have a V function like Chunky-Schlebike-Fusco with V positive of finite volume. You consider a concentration set for the singular derivative of V, so the Cantorian and the jump part. And you assume that the set where V lower is equal to 0, union with K, does not disconnect V positive. And I have to put it between quotes because, okay, this V hat equals 0 is pointwise unequivocally defined for every V Lebesgue equivalent to every other V, okay? Yeah. So yeah, it's a, yes. Concentration set means that outside of that, the measure doesn't do anything. So, so this guy K, right, is defined only Hn minus 1 everywhere. So I can, if I take out or add the set of Hn1 minus null measure, Cantor will not see it, jump will not see it, so I can do that. I will still have concentration. It's completely free. I can trade them easily. I have to be careful trading something of Hn minus 1 positive because I may lose a part where the function is jumping, or higher because the Cantor part could be there too. So, but let's say that this Borel set, which is only defined modulo Hn minus 1, does not disconnect V positive. But again, V positive is just defined Lebesgue, in the Lebesgue sense. So if I would, so the question is there a workable definition of does not disconnect that allow me to prove that under these conditions, rigidity holds? Okay? They are Lebesgue equivalent, so you could do that. So here you want V hat because here you want something that it's already in the range of Hn minus 1 precision. There it doesn't matter. There on the right-hand side of this proposition, it's fine to have something just Lebesgue defined. So I can put anything that is Lebesgue equivalent to V can be put here, same statement. I've just put there the simplest symbol I can put there to make the statement correct. All right. Okay. Oh, this is what I was just saying. K defined modulo Hn minus 1, V positive defined modulo Lebesgue. So what does it mean does not disconnect? Okay, this is the definition that we have proposed in that paper. So, bit of notation. When I have a Borel set G and the number T between 0 and 1, G, T between parentheses will mean the points of Lebesgue density T. Okay? And the essential boundary of G will be the complement of the points of density 0 and density 1. So from the point of view of measure theory, density 1 is like the interior of G, density 0 is like the complement of the closure of G, and so the measure theoretic boundary is what is left if you take out the two. Okay? So this is an important object, again, because it's uniquely defined in the Lebesgue equivalence class of G, right? So if I take G, I take a Lebesgue equivalent copy of G, I got the same G0, the same G1, I got all the same GTs, so I got the same essential boundary. And it's an important object because if that uniquely defined object, sorry, not uniquely, stably defined object is a Hn minus 1 finite if and only if this guy G has finite perimeter. So it's a particularly important object in measure theory. And now the definition. So what does it mean for a Borel set to essentially disconnect another Borel set? And here, I will explain the definition in a second, I can come up with 5 different definitions of what that may mean. So the point is not proposing a definition that I like. The problem is having a definition that works. And I don't see any reason why what works in one problem, so this definition is going to work like magic on symmetrization theory. When we came up with this definition, we had no reason to believe this definition would have played any role in any other problem, okay? So that's what was quite surprising for me. Okay, so a Borel set disconnects another Borel set if there is a Lebesgue partition of G to sets G plus and G minus. They are Lebesgue disjoint, their union is Lebesgue equivalent to G, and they're both non-trivial, they're both positive measure, otherwise it's not really two pieces. Okay? So I have these two pieces, G plus and G minus. I look at their common essential boundary in the measure theoretic interior of G. So if you look at the picture, right, G plus is this thing here, G minus is this thing here. So of course, the essential boundary of G plus as a part here, the essential boundary of G minus as a part here, but I'm not interested in those. I'm interested in the part of their boundaries in G1. So essentially, I'm talking about this line here. Okay, this will be for this trivial example. Okay, so we want the existence of a non-trivial partition which modulo Hn minus 1 is contained in K. Then we are fine. Then K essentially disconnects G. So, for example, say that I have something that disconnects in the sense of topology. So this would be a closed set that disconnects this open set G because there are two non-trivial open sets, right? And the common boundary of these open sets is contained in my set K. I could have taken K even a bit bigger, right? Adding something that was needed. Still the inclusion holds is still disconnecting by using G plus and G minus. All right? However, now say that you take out of this K prime a set of H10. Imagine this was a segment, I take out a counter set or all the rational numbers. Then it doesn't disconnect anymore in the sense of topology because I'm creating a ton of holes. It still disconnects in this sense. Okay? That's all there is. Huh? Okay, so I think the definition is clear, right? I mean, I have two pieces, I look at two non-trivial pieces, they have positive measure, they define an interface inside my Borel set G by using the essential boundaries, and K disconnects if it contains this interface for such a pair. Then it's able to disconnect G in the essential sense. Yes? There is a relation as soon as you start, for example, if you know that K here is Hn minus 1 finite, then G plus and G minus are sets of finite perimeter, right? So you can relate, you have to relate all this story with the theory of indecomposable sets. The problem is that when you do symmetrization theory, many of the objects you deal with are not rectifiable or have finite Hn minus 1 measure. So, for example, yeah, this is really a tangential direction, but so you really need this kind of flexibility to do symmetrization theory. You really need to be able to work. And then if you can recover, for some reason, finite Hn minus 1 measure, these pieces have finite perimeter, and then you can see it as a, okay? For example, we say that a Borel set is essentially connected if the empty set does not essentially disconnect it, right? And being essentially connected is equivalent to be indecomposable if your set was a set of finite perimeter. Okay? This, I think, answers cleanly the question. But you need these few bits more of terminology and, okay, to go by. So, again, it's very stable because if I change G on a Lebesgue set, fine. Lebesgue null set, fine. I don't change anything. And if I change K by a set of n minus one dimensional measure, I don't change anything. So it's definitely stable by the things that I care about. But this is not the point. I can give you 500 definitions that are stable. Is this related to anything I care about? And the answer is yes. This is one of the many theorems we prove with Cagnetti, Colombo, and De Filippis. Is the theorem you would have guessed is true. So if V lower equals 0 and the concentration set for the singular part of the derivative essentially disconnects. Oh, no, this is wrong. Do not essentially disconnect. I'm sorry. I will need to correct this, okay? So this is kind of the opposite of what it should be. So if they are not able to disconnect V positive, then you have rigidity, okay? And then, for example, in that paper, if you're curious, you can give characterizations, like rigidity holds if and only if V does certain things. Okay, but it's a bit more complicated. So I mean, I don't need to, I just wanted to give you a motivation. So where this essential disconnection idea comes from? It comes from this setting. Okay, so now let's do the measure theoretic homotopic spending. So we have our closed set. We have our class C of embeddings of S1, and then we introduce a new object, T of C. So these are the tubes associated to the curves. So what is a tube? Is a triple, gamma phi T. Gamma is a curve in C. Phi is a diffeomorphism from S1 cross the closed n-dimensional ball into omega, so that phi, the slice of phi corresponding to the center of the ball is gamma itself. So you're like extending gamma to a tube, okay? And of course, each fiber, so if I fix a point in the ball Bn, and I go through S1, I have just one homotopic copy of gamma that is still in the class C. So it's like a foliation of a tube of a neighborhood of gamma, right, by cars that are still in C, okay? So that's what one of these tubes is. And you call T simply the image through phi of S1 cross the open ball. So T is open. And then for every point S on S1, you will have a slice, T of S. So the slice of the tube corresponding to little s, right? It will be this sort of disk. It's not really a disk because this is just a diffeomorphism. So it will be a set that will kind of look like a diffeomorphic image of a disk, okay? So this is the notation. So it's just going slow because these objects will come over and over and over. So gamma, phi, T, and T of S, okay? And this function that parameterizes the tubular neighborhood, okay? So tentative definition. So we're going to say that a Borel set is a C-spanning W. I should say, since I already have a notion of C-spanning for closed sets, I should say is measured theoretically C-spanning. That at the end, everything will be equivalent. So I spare you the pain. I just say S Borel set is C-spanning if for every triple gamma phi T in T of C, and for almost every slice, there exists a Lebesgue partition T1 and T2 of the tube T, of the open tube, so that, the interface generated by the partition, right, is contained in the slice S union your set capital S, and contains the slice itself. So what I'm really saying is that S union the slice essentially disconnects the tube, but in doing so, it uses T of S. Okay, so there is a partition that makes use of T of S, end of S, and then it creates two pieces, T1 and T2, that disconnect the tube. Tentative. But this is the minimum. So you see where I'm going, right? I am replacing a pointwise condition Now I start having solid objects. I'm relaxing the thing a bit, okay? It's becoming a bit less topological already and a bit more measure theoretic. And so if you want in a sentence, S union for almost every point in S1, S union the slice, corresponding slice, essentially disconnects T by essentially using the slice, okay? So I'm disconnecting, but in my disconnection, in my disconnecting interface, I want to be sure that I'm using the slice, okay? Does it make sense? Questions? Yeah, but that's what it is, right? This is the definition of this, this is exactly what we're doing. So there is this phi, it kind of ties them together, yeah. That's a possibility. I'll come to that. No, I don't think it's the same. Another possibility, let me throw another possibility immediately. I could say that Hn of S intersected the tube is positive for every tube. Why not? So that's exactly, no, that's perfect. That's exactly my point. You can come up with, how many here in the room? 40 people. So we can come up with 40 slightly different definitions of what it means to measure, or with Vincenzo even more, of measure theoretic homotopic spanning, right? Because it's just a definition. Who cares? Is it stable by Hn? Yes, because I'm just, right? So that's not the point. The point is this going to give us stuff like compactness theorems that, I mean, then the challenge is proving theorems, okay? So when you see this thing, you have no reason to say yes or no, I take it or I don't take it. You prove theorems. So that's what we were doing. So we were, okay, we said this is the right one. So you start proving that on a closed set, this definition is the same as the Harrison and Pugh definition. And then you can't close the proof at a certain point. There is something that never works. Then you try to understand what is an example where it doesn't work. Tentative. This is the example. So this is W is just a torus. S is the disk with 3 holes. There are 3 holes in the disk. Through the 3 holes, you make pass through a curve that has link number 3 with W. 3 or any odd number, if you want to see where it's going. But I mean, 3 is enough. 1 is not enough. 3 is a smaller odd number I could put there. So this curve is linking 3 times, and then it comes back, right? So, and I do a neighborhood of this curve, I call it U. So U will be an open neighborhood of a curve with link 3 to W. I do the open neighborhood, and then I defined S to be the disk minus U. So I have done 3 holes in the disk, and then I am adding the boundary of U. So that's a weird surface. So it's a disk with this thing, okay? Why not? Then I put a tube. This is one admissible tube. Is a tube that contains, so a tube means an epsilon neighborhood, a positive neighborhood of some curve that I can parameterize, some curve in the class C. Absolutely, I can find, this curve here, and this will be the neighborhood, and I have a parameterization, and so on and so forth. Okay. So what is the characteristic property of this tube? Let me see what I want to say here. Yeah. So when you have a tube like this, it has this weird property that if you take a slice of way more than almost every slice, a lot of slices of this tube, when you intersect them with S, okay, will give you the boundary of 3 disks. So more correctly, when you intersect them with U would be the interior of this tube around the curve with link 3. So when we intersect T with this thing, we get D1, D2, and D3. We get 3 disks, right? For most slices. So if I slice here, I look what happens to U. U minus TS will be the complement of these 3 disks. And U minus TS will have 3 connected components, A1, A2, A3, that I have colored in yellow, green, and purple, because otherwise it's hard to see them. Okay? I mean, so far, it's just cool pictures, right? And we are fine with that. Good. No, but I mean, I'm kind of building to the point where we see that doesn't work. Now, let's assume that there is a non-trivial Lebesgue partition T1 and T2 with the property that we want. So this partition will generate an interface. This is the interface, right? And the interface is going to be contained in S union TS, and it's going to contain the slice. If, S is spanning, this must be happening. Okay. So, what we would be saying is that S union TS, so if this can be done, so essentially if S union TS can disconnect the tube T by essentially using TS, this property can be localized inside the open set U. Remember that U is the interior of this tube, okay? So consequence of this is that if this guy, if S union TS essentially disconnects T by essentially using TS, then the same holds localized in U. It's not immediate, it's just intuitive. Then you have to prove it. I mean, it's a whole story. But so S union TS intersection U essentially disconnect the part of the tube that is in U, and you simplify immediately this assertion. Why? Because what is the part of the tube which is in U? It's U itself. What is S union TS intersection U? Is just whatever the slice is doing in U. And what was the slice doing in U? 3 disks, D1, D2, and D3. So, moral of the story, if our definition predicts the right thing, this guy is spanning, so it must be spanning according to the definition, and then you localize this construction, then you find the following assertion, that D1 union D2 union D3, so the 3 little disks in bold black, essentially disconnects this tube by essentially using themselves. Essentially, you're saying that these 3 disks are the interface generated by a partition of 2 pieces. That's what you're saying. And that's not possible. Because, so should it be true that D1 union D2 union D3 essentially disconnects this thing by using itself? It means that there is a Lebesgue partition U1, U2 of this thing, U, whose interface is exactly the 3 guys, D1, union D2, union D3. However, it's impossible because what is this essential partition? It's some combination of the 3 connected components, A1, A2, and A3 of U. You have to combine them to get U1 and U2. But, for example, you try and do U1, you define it to be A1 union A2. But if you do that, as soon as you take the union of 2 of them, you are erasing a disk. And so it doesn't work. It can be done. As soon as you try to pack these 3 connected components into 2 pieces, you are eating up one of the 3 disks. So you cannot find 2 pieces that generate exactly as their interface those 3 disks. It's just a, what is that, combinatorial problem. I don't know. It's like 2 and 3 don't talk together. Okay, so you can't do it. However, if you think a moment more about it, you can do it in pairs of 2. So let me show you the actual definition and then, so this is the tentative definition. This is the actual definition. So the actual definition, you have to ask this. Tentative was for every triple and almost every little s, we have this partition. It becomes for every triple, for almost every s, you have the following property. That for Hn almost every x in, it would be in Ts, in the slice that you are considering. I've missed the other information. So for almost every point in the slice, you can find a partition that contains that point. So rather than asking that I can find a partition whose interface contains the whole slice, I am saying I can find for almost every point, I can find a partition that contains that point in its interface. Kind of less ambitious. And this clearly works in the previous example. Because you see, although I cannot find one partition that does everything, I can definitely find that these three disks essentially disconnect you by essentially using two of them at a time. So if I want to cover a point in D1, D2, I can do that. I cannot just do in one shot all the points in D1, D2, and D3. But I can do in one shot all the points in D1 and D2, or all the points in D2 and D3, or all the points in D1 and D3. So it's a bit less dramatic than this definition that says that for almost every point I have to find a partition. It's going to be more like I have to take the slice, divide and conquer a bit, and certain pieces of the slice will work with certain partitions. So it's a bit less dramatic than this definition seems to suggest, okay? But this is the first time I can present this work in 6 hours, so I wanted to give you the real thing. So this is so when I give this talk here, it's like, there is this thing, measure theoretic, and we move on, okay? So this is, let's like take 30 seconds. So this is what it is. So this is what is behind this work. So if you don't do these, I really don't know how to prove these theorems. And this is the measure theoretic homotopic spanning. So that's why I had to do lecture number 2 with the subfield capillarity theory with intersecting curves, because unless you have a strong motivation, why would you try these, you know? I mean, it's horrible. So, okay. We have the definition now. Then there is a theorem that tells you that topological and measure theoretic homotopic spanning are equivalent on closed sets. One implication, it's easy. Topological imply measure theoretic. The other one, it's a bit of work, as you can imagine. But it's so you are definitely extending the old definition. But again, that's not enough. There could be 500 ways to extend the topological definition. That's compatibility check is good. So now the point is that we are going to do all the things we did before and more, okay? Essentially by using the theory of sets of finite perimeter. That's it. We will not need anything fancy anymore. So, yes. Mm-hmm. Mm-hmm. Let me, yeah, this is the tentative definition. Small doesn't change anything. No. It wouldn't bring, I mean, longer definition for sure, but it doesn't. No, okay, but yeah, but you want the thing to be equivalent on every set. No, you want the definition to be equivalent for every set. So it's like if you want to say it like for every tube, I can find a set that it's spanning and doesn't span according to definition. You can. You can do a very fine tube, and then inside this very fine tube, put a curve with odd link that is contained in the tube. And then the U around that curve is going to generate such an example for some S. No, there is no way around it, I think. I mean, it's good asking if one can save work, but at the end of the day, I think you... Okay, so, and now we do subfield capillarity theory, take 2. Because now we can make Borel sets span. So why caring about taking the closure of the reduced boundary as I had to do before? Now I can say the reduced boundary is spanning. So this will be the capillarity theory. So this first line here, this psi, and there is a BD down here for boundary. So this is the problem we studied with King and Stuvard. So it's the capillarity energy, Hn of omega intersection the reduced boundary V, so the perimeter of V in omega, for set with volume V, such that omega intersection the reduced boundary of V, C spans W. So this is exactly what I was doing yesterday. Yesterday, I had to do the closure of the reduced boundary because C spanning made sense only for closed sets. Now I don't care anymore because I have a definition that is equivalent, and I'm crossing my fingers that it will work when I will take limits, you know, but at least I try. Then I can say, okay, what was the relaxed problem? We already know because we did the previous paper, right? So we know what to expect. The relaxed problem should be pairs kappa E so that the reduced boundary of E is contained modulo Hn inside of K. So it's really the guys that I was drawing the other day, okay? So stuff like this. So this will be kappa E, and kappa contains the boundary of E, okay? It's the whole thing. And also stuff that is not in the boundary of E. So, and you have this containment, K and E are Borel sets, and then you have an effective energy that we have computed yesterday, is the Hn measure of K minus the reduced boundary plus the perimeter of E. Okay? So this part with multiplicity 2. So these are the objects that we were studying yesterday, but recast in without having to worry about taking the closure of anything. And then there is a parallel theory that rather than boundary will become the bulk theory. So it will have a subscript bk. Sorry, this is a bit of a dense slide, but that's what it is. So this is, again, capillarity theory. So this guy is the same as the first line. The only difference is the set that does the spanning, which is here. So now I am not asking omega intersection the reduced boundary to do the spanning. I am also adding the point of density 1 of E. So this would be, in topological terms, like saying omega intersection the closure of E. So the closure of the droplet inside the container does the spanning. But I don't work with closures. I don't care about topology anymore. I work with point of density 1, union reduced boundary. It means the measure theoretic modulo Hn means the measure theoretic closure of the set E. So this is the guy that does the spanning. So this is the measure theoretic version of the Gauss capillarity theory with bulk spanning. And then I just guess, what will this guy relax on? What will be the effective energy when there is collapsing? It's going to be very similar to the effective energy I had before, right? Only that, only the part of K outside E1 will be in the effective energy. So I don't expect anymore to see interior collapsing, essentially by construction, because I really don't need it, okay? That's just my hope. I have to prove it. But I mean, at least it seems more likely. So you see, rather than doing K minus reduced boundary V, I do K minus E1 union reduced boundary V. I could have written there, and it would be exactly the same energy, the first term. I could have put twice Hn of K intersection the points of density 0. Because there is a theorem of Federer that tells you that for a set of finite perimeter, okay, E0, E1, and reduced boundary, or E0, E1, and essential boundary are an Hn partition of Rn plus 1. They are all there is out there, modulo Hn. So taking out E1 and the reduced boundary is like localizing outside of E in measure theoretic sense. So I could have written intersection E0. Okay? So this is the effective energy. So this script F bk. And who is doing the spanning in the relaxed theory? So in the non-relaxed theory, it was the measure theoretic closure of E, and now it's K union E1. I don't have to write union the reduced boundary because the reduced boundary by construction is inside K. So that's what this class of pairs come with. They come already with the reduced boundary of the set E contained inside K. Contained, again, modulo Hn. Right? Before, each time I was doing this game, I had to check that the closure of the reduced boundary was inside the closed set that I declared as my K. Now, who cares? It's just Hn contained. Okay. So there is a theorem by Novak, my ex-postdoc that was working on this project. As a side paper to this whole thing, he has a standalone paper where he proves that psi star is the relaxation of little psi star, both for star boundary and bulk versions. Okay? So if you don't know what is relaxation, essentially it means you're doing the same variational problem. It's the same thing. You can start from the capillarity or you can start from the generalized. You're going to find the same infimum. And this guy, you expect to have always minimizers, the other one maybe not because there is collapsing. But that's all there is, okay? So this relaxation theorem tells you that you can't really study this without caring about that. So you may directly study that, okay? And then ask yourself, when is it that the minimizer of the relaxed problem is a minimizer of the original problem? Okay, so there is a direct method for this whole thing. So let's take the wireframe, the homotopic class C as usual. Let's take a sequence Kj, Ej, with a reduced boundary Hn of the Ej's, Hn contains in the Kj's, the Kj's with bounded areas. Let's consider the limits. So these limits, I'm assuming, but I could just get them by compactness. Okay, so I have an L1 lock limit E for Ej, and I look at the limits for the measures I care about. So this is mu boundary and mu bulk. Mu boundary is what is the driving energy in the boundary spanning problem. Mu bulk is what is the driving measure. So these are the measures for which that you use to do compactness in the existence proof, okay? And their radon limits. Okay, is it clear what are these things? I'm sorry, I don't know if I'm killing you, how much I'm killing you. Okay, so if you're already desperate to leave the room or... this stuff, it's heavy, I don't know. Okay. Then you don't need to define anything anymore. So now you can declare what are the limit sets K boundary and K bulk. Okay? These guys are just going to be the reduced boundary of E. You have to include them because that's by construction, you want it to be there. And then you get the points that are not in the reduced boundary, but where the density of the relevant limit, for example, the density of mu boundary, the limit of these collapsed boundary measures, have upper n-dimensional density greater or equal than 2. So these are the points where greater or equal than 2 means collapsing has happened, right? We had a sequence of sets of finite perimeter, they carried measure 1, and then stuff starts piling up. You see at least 2 of them. So here I'm saying, in this limit of Kj, Ej towards this set E and then some K, but with K, okay? I have to tell you what is the limit K. So if I'm working with the boundary or with the bulk, I declare different Ks. The K I declare for the boundary case is a set where the limit radon measure has density at least 2. So there could be a lot of piling up, but definitely not the boundary V. So it's like when you do varifold convergence and you try to say the set where the limit varifold will have seen some collapsing. So these are the only possible reasonable choices. So, and then the theorem is that you have lower semi-continuity. So the boundary energy is more than the boundary energy of KBDE. The bulk energy of KJJ is more than the bulk energy of K bulk E. And you have closure. If the KJs were spanning W, which would be the case you're interested in the boundary case, then K boundary is a C-spanning set. If Kj union Ej1 spans W, which is the condition you would care if you're doing the bulk theory, then this guy is smaller. So K bulk is smaller than K boundary, if you go back to the definition. So K bulk, it's smaller because you see I have less point to play with. I also play with a different limit, but the limit that I'm playing it is a measure that is smaller because I'm taking out more stuff. So it's like less points. So these less points are still spanning. Why? Because they're assuming more than Kj union Ej1 is spanning. So this theorem is useful because it's a sort of very general, openly constructed sandbox for taking these limits with collapsing in these kind of problems. Maybe you will have other problems with different energies, okay? But the closure of the spanning condition, you can get it from here. And yes, so this observation is for the next theorem. Well, for the first line of the next theorem. So let me say this. So with this theorem, to prove the existence of generalized minimizers, it takes nothing. So you don't have to do smart competitors, cap competitors, con competitors, and all variants of sorts, okay? No. It's just compactness of sets of finite perimeter. Where are the sets of finite perimeter? Is that locally, right? You look at this Kj, it's a Borel set. You do this Borel set and the ball, and you show that there is a partition of sets of finite perimeter associated, a sequence of partitions. The sequence of partitions, they have a compactness in the sense of partitions. And now, since the measure theoretic homotopic spanning is measure theoretic, this is all compatible, and it's kind of becomes easy. Okay, so this is stuff you don't need to do price theorem. No need for price theorem anywhere in this proof. And definitely not even the tools that we have used to replace price theorem when doing the anisotropic Harrison-Pugh problem and so on and so forth. It's completely elementary. Elementary in the sense that just basic sets of finite perimeter. So this is quite relevant for me because it's like proving the whole, for example, the whole paper we had on CPAM for the existence of the soap-fin capillarity model in, I don't know, 8 pages total. Of course, it's 8 pages total if you mindlessly check the proofs and you don't so you really have to do work to come up with these notions, okay? But once you have them, it's like very, very quickly go to the goal. So I think this is essentially the right way of doing these things. So that's the bottom line. I think it's fair to say that it's the right way of doing these things. And then you start proving cheap regularity. So Allard and trivial considerations. And you get that you don't have interior collapsing in the bulk theory. So let's look at the bulk theory. There exists a minimizer. Once you have a minimizer that will just be a pair of Borel sets, K and E, you can start cleaning it up. So modulo Hn modification of K and modulo Lebesgue modifications of E, you will be able to assert that K is closed, E is open, the closure of the reduced boundary agrees with the topological boundary, which is not true in general for a set of finite perimeter. There could be a Lebesgue positive measure difference between the two. They're the same. They're bounded. K union is spans, but most of all, there are no points of K inside the density 1 of E. So there is no interior collapsing, which is nice because we didn't believe it. So it's nice that we were able to get rid of it in this bulk theory. But again, I don't see, from the point of view of modeling, I don't see why you should prefer the boundary theory to the bulk theory. So why saying that in the capillarity problem, the boundary of the droplet spans or the whole droplet spans? I mean, it doesn't seem to make any difference physically. So let's work with the bulk one so that we don't have interior collapsing and it's nicer. And then K is the disjoint union of K minus the boundary of E, K in the boundary of E and outside of the reduced boundary of E, that is the transition region, and then the reduced boundary of E. So you have these 3 pieces. What you can prove about these 3 pieces is that, okay, K minus the closure of the boundary of E is a smooth minimal surface, if n is less or equal than 6, otherwise you may have the canonical singularities. The reduced boundary is a smooth CMC surface, and this we knew. All these 2 things, we knew them, right? Even in the previous theory with the classical homotopic spanning. But again, remember to prove this smooth minimal surface, I had to do the argument with wetting the Y point and recovering the volume. All that is going to be gone. Even more. It's quite incredible. So the transition region that in the previous iterations was this meager set. Now we can say that if it's non-empty, if you have 1 point there, then the Lagrange multiplier is negative. Moreover, locally, near a point of the transition region, K is the union of 2 C11 graphs that detach tangentially at X. So this is the continuity of the normal conjecture assumed by the physicists. So first you do the regularity of K. So K detaches in a C11 tangential way. And then you use the theory, PDE theory of free boundary problems to say that the transition region itself, so locally near every point of the transition region, K is the union of 2 tangentially detaching graphs. And then the transition is decomposable as the union of a C1 beta n-dimensional surface. So in the case that we care about, n equal 2 in dimension 3 is a line, C1 beta line. And then what is left is a closed set that is stratified into k-dimensional rectifiable sets. So it's a huge salad of words. What it means that in R3, the transition region is a C1 beta line plus finitely many points. So there could be singular points on the transition line, but they're locally finitely many. Yeah. No, the whole case. So that's the point. So the reduced boundary of E, so in this picture, the reduced boundary of E would be this circular arc. This, it's a smooth CMC surface. Then you know that there is K minus the closure of E, K minus this point. You know that this is a smooth minimal surface, right? The problem is that what is a point in the picture could be a set of positive area. You just know it has non-empty interior. This could be huge. And not only could be huge, but who tells you that they attach like that? It could be, I don't even know what it means that they attach, because they're attaching through a set of positive measure. I really don't even know how to imagine this thing, okay? So it could be that it opens up and down many times, right? It could be that, for example, K does something like this, ta, 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 ta. And I don't know. So it could be a... So what we are claiming, first of all, is that at each of these points, there are coordinates, and there is a function U1 and a function U2 that are C11 functions, okay? And your point, yeah, so you just, essentially you claim that the picture that you would, that the physicists actually assume and use, page 5 of the book, is correct. And it comes from capillarity theory. So it's not that you assume it because you see it and you say, I want to work like this. It's like capillarity theory by minimization and relaxation leads you exactly to what they're assuming. There may be singular points. Now, are there? I don't know. But the transition line may have, from what we can download from the free boundary literature, may have isolated singular points in R3. No, okay, W here is just a closed set. So the assumption of this theorem is that the Harrison-Pugh problem is finite energy. Yeah. So for sufficient, let me think. Yes, this is a consequence of theorems that we have just proved. So because you know that the Harrison-Pugh minimizer is in the convex envelope of W, because it's the support of a stationary varifold in the complement of W. And then, I will talk about this tomorrow, we have proved recently, by building on this recent stuff, we have proved that as the volume goes to 0, the minimizers of this problem converge in Hausdorff to the Harrison-Pugh minimizer. So since the Harrison-Pugh minimizer is containing the convex envelope of W, if the convex, so now, okay, you have to work a bit on it, but you get the idea. Okay. So yeah, eventually also that is true. Yes. But I mean, it's you have to get there. So the key points. So by doing the measure theoretic overhaul, you have passed from working with these, which was not even this because there was the closure of the reduced boundary, but remember that in the previous iteration of this problem, all we knew was that the effective energy, the relaxed energy of the generalized minimizer, were less than the energy of every competitor in the original problem. Which, as I told already, it meant whenever I wanted to say something about the minimizer KE, I had to do a competitor of KE, then do an epsilon neighborhood of this guy, use some Minkowski content to Hausdorff theorem to estimate, to construct a sequence of sets F whose energy was going to the energy of the competitor I wanted to use. Now that you have done this thing, you directly land, you can directly modify K into HF, okay? And you compare the energy. So you but this is important because Minkowski to Hausdorff needs assumptions. It's not true in general, okay? So you really need assumptions to make it work. You need density estimates, you need rectifiability. So it's a delicate object to use, okay? Then And this is the key point. The other key point is not only that we have replaced F boundary less than Hn with inequality directly on the relaxed energy, but that in every ball inside of omega, B minus K and E, the union of K and E, can be decomposed into finitely many sets of finite perimeter. Each of them is going to be a lambda minimizer. So if I take again my example, right, and I still have to do the regularity theory, so I put a ball in this bad region. Here the transition region could be a mess. This is E and this is K. What we can prove once we have these setting, measure theoretic setting and partition setting, is that K minus E out of the ball U1, U2, and U3, the sets that are left out are going to be sets of lambda minimizers of the perimeter. So lambda minimizers of the perimeter, maybe, yeah, I gave for. So lambda minimizers of the perimeter, it means sets that, so a set U is a lambda minimizer of the perimeter in an open set. If for every ball in that set, you minimize the perimeter, so a ball of radius R, say, with respect to any competitor V, plus an error that goes like, say, the volume of the ball. So what is the idea? That this is order R to the N, okay? So it's like being a minimizer of the perimeter, so being an area minimizing surface, plus an error that has sufficiently small scales should disappear. So, and this is a theorem from 1986, the lecture notes of Tamanini, that lambda minimizers of the perimeter are C1 alpha, have C1 alpha boundary in dimension up to 6. This is 1986. It's like 40 years ago you could do that, okay? So that's all you need. I'm sorry to stress that, but you have to understand one point. So this idea of having multiplicity 2 and then detaching and having multiplicity 1 while you solve a distributional PDE, zero mean curvature, constant mean curvature, it's there, okay? So, and we have all been trying to understand it using varifolds. When you work with varifolds in this kind of regularity theorems, the big challenge is showing that if you start from a point where you have a decent density area assumption at a sufficiently small scale, you're going to see graphicality. This is the problem, okay? That tells apart good points from singular points. And doing this on varifolds is extremely delicate. So if you go and check the papers by Vikar Mazekera and collaborators, these are extremely delicate work to understand how you have these multiplicity and then you detach. And you have a drop in multiplicity and a geometric distribution of the multiplicity, right? I mean, Reinaldo here is an expert of area minimizing currents with modulo P in higher codimension and all these sheeting problems. I mean, this is where it becomes extremely delicate, honestly, right? So what is incredible in that for this problem, which however is physically relevant, at the end of the day, you go back and use the Stone Age tools, right? Because this is the starting point of the theory if you study regularity theory for geometric variational problems. So, and so let me try to just give you a picture here. I hope you can see up there. Maybe it's a bit small. Yes. Mm-hmm. Yeah, because that thing, yeah, because, yeah. No, yeah. So the problem I see is, yeah, local partitions. Yeah. Okay. So I don't know. I mean, it's essentially what I'm doing. At the end of the day, it's essentially what you discover is that, so, yes. Okay, but how do you? So you see, I think it's like you're asking me. why are you studying minimal surfaces using currents when at the end of the day they are locally graphs? You should work with PDEs. Yes, but at the end of the day, so you have to get there. So I think there is a bit, yeah, there is a bit of that. So at the end of the day, everything is nice, and because the regularity theorem holds, and we can sleep well, right? That's how it always ends after a while. So yeah, but I guess that the point is getting there. So I'm not really sure if there is a, there could be a way of reformulating all of these that is more tailored to this problem. And what? Yeah, I know, of course. So anyway, so let me try finally to explain this point. So let's say that we have a ball, and okay, we have our ball K and E, and we look at the three components UI, UJ, and UK that are left outside of the ball by K union E. Okay, so you will have a formula easily that tells you, for example, that the bulk energy or the boundary energy, for this example, they are the same because there is no interior collapsing. Okay. So the energy that we study is essentially the sum of the perimeters of the three sets, right? Because when I sum the perimeters, this bold line is counted twice, while the boundary is just counted once, right? So UI, UJ, UK. And now let me take a competitor, VI, VJ, VK. So actually, I'm taking, you see, I want to take a variation VI of UI. So is this the set bounded by this wiggly curve, right? And then given a variation VI, so this is the guy that is given, is VI, I have to define VJ and VK, and I have to define a pair K prime, E prime, you see? So that I get a competitor and the decomposition of this competitor. So I am replacing UI with this set VI. How do I define the new K prime, E prime, and the new sets? So by doing as it's done in this picture, you see, I don't have anymore the boundary of UI. The boundary of UI was doing this. It's not there anymore. But I found a way to still have the boundary of VK, sorry, of UK. The boundary of UK was these two segments and this circular arc. They're still there. The segment is still here. The circular arc is still here. It's just that, for example, the circular arc, right, was in the boundary of UK, and now it's a bit of it in the boundary of UI, a bit of it in the boundary of VK, kind of redistributing each piece of perimeter, right? Same for the boundary of UJ. I have kept all of the boundary of UJ. It's just that it's not in the boundary of VJ. I have to trade a bit. So to do the boundary of UJ, I have to use a bit of VJ and a bit of E prime of the new set. Okay? And then I have lost part of the boundary UI, and but I have got all the boundary of VI. So the new pair K prime E prime has the sum of these three perimeters, and when I take the difference of the relaxed energies, f of K prime, f of K, what I get is just the difference of the two sets I care about, right? UI and VI. And why do I get not just straight minimality, but lambda minimality? Because I have to adjust the volume. Because you see, when I start doing these trade-offs, I add stuff, I'm also modifying E in this ball. So I'm definitely messing with the volume. Somewhere else, I will fix the volume, of course. And that's the lambda Rn plus 1. All right? So, but now you wonder, okay, nice. You got but how on earth this didn't screw up the spanning? Because I've thrown away the boundary of, part of the boundary of the set UI is gone, right? And that's where the measure theoretic thing comes in all its glory and saves the day. Because you have a measure theoretic version of the entry-exit component lemma that we discussed the other day. So remember that to make all those competitors we were discussing work, we had to say something like this. So let's have a ball, let's have a minimizer in the, or element of a minimizing sequence in the Harrison-Pugh problem, right? And we said, okay, let's say that I do some modification inside here of this set, whatever I want to do inside the ball, okay? But so when I check that whatever modification still intersects a curve gamma, if the intersection of the original curve gamma and S was happening outside of the ball, it was fine. It doesn't matter what I do inside the ball. But if I was modifying inside the ball, and sorry, but if I'm working with a curve gamma such that the intersection of gamma and S outside the ball was empty, this could potentially be trouble because I'm changing inside the ball. So the key was saying that if a curve gamma doesn't intersect outside of the ball, then it must have an interval inside of it that is coming in from one connected component of boundary of the ball minus S, whatever S is doing here, okay? So boundary of the ball minus S will have some connected components, and the curve must enter from one point and exit from another component. Why? Because if it comes in and comes out from the same component, I can homotopically move it away, and I wasn't intersecting outside. I'm not intersecting inside, I wasn't intersecting at all, contradiction. So this was the key topological lemma to do all the competitors. Being sure that the curve comes in from a connected component must come out from another connected component. And then the cap competitors are good, the cone competitors are good. In the papers with King and Stuvard, the slab competitors are good, and all the sort of machinery we had to create, they're all good, because you can always check that you didn't mess up the boundary components, but for one. And here is the same, because at the end of the day, we were be able to preserve, and this is the measured theoretic version of it, we were be able to preserve the reduced boundary of Uj and Uk are still part of the set K prime. So you see the reduced boundary of Uk and Uj have been still saved. So, and as soon as you lose only one of these guys, that's the key point, right? As soon as you, in your local partition of the ball, you lose only one of your element of the partition, you are still homotopically spanning in the measured theoretic sense. So you have a measured theoretic version of that thing. So locally, K union E, it's spanning, right? Locally in a ball, it has, in general, countably many connected components that are just indecomposable sets of finite perimeter. And essentially, you look at the boundary of these guys in the interior, whenever you throw away the reduced boundary of only one of them, you're still fine, you're still spanning. Why you should believe that? Because it's very similar to that topological thing that was easy to visualize. And then you prove it, but again, it's once you have the right definitions, and this is why they are the right definition, because they allow you to prove these things. So, okay, but this is just why you get this lambda minimality. And once you have the lambda minimality, it's done, it's easy. Okay, so I will tell you tomorrow the original motivation. So tomorrow I will give you the even more recent results, so the results that are not written yet, but we are writing them, to give a bit the state of the art. And I will talk about the original motivation of the problem, but I want to tell you immediately one thing, and then I'm done, which is super cool. So you may wonder, okay, but this is extremely fishy, right? Because, okay, this guy is doing with sets of finite perimeter the regularity theory for everything, right? So, but then what's wrong with the y points of Taylor, right? Because you are in the original Harrison-Puig-Plateau problem, there is the set U1, there is the set U2, there is the set U3, and these guys are definitely not lambda perimeter minimizers, because otherwise they would be C1 alpha sets. They're not C1 alpha, they have a corner. So why can't you use all these magical tools and say, let me take a variation of U1, call it V1, and then define some set S prime that cuts out some sets V2 and V3, so that those same analogous inequalities hold. And then by magic, I discovered that U1 is a lambda minimizer. So why can't I do that? That's super cool. Because to get away with that, I have the set E prime. So in these formulas, E prime acts as a trash can for some of the terms that I don't know what to do with. And then, since I have a volume to recover, you know, it's like I use the fact that I can add stuff. I can create a set. Then somewhere else I will recover the volume. So it's a bit crazy. It's like you cannot do the Taylor theorem, even though the Taylor theorem is just this partition game, if you want to see it as a partition game. But the lambda minimality is really using the fact that there is a positive volume. Who is going to be the lambda in the lambda minimality? The lambda in the lambda minimality is going to be the constant you get from the volume fixing variation applied to some other part of the wet object, which means essentially that you're using an object with super high curvature, because we know that these lambdas are going to minus infinity at the end of the day when the volume goes to 0. So you can't even hope to use this theory to approximate. Of course, it's all obvious, right? To do the regularity of the limit problem. You can't, absolutely, you can't. Of course you can't, because the lambdas that are involved are sensible to the volume that is small. They will be inverse to that volume. They will be huge, okay? So it all adds up. In a sense, this trick really relies on the fact that there is a positive volume. It's a sort of regularization effect, as we knew from the beginning. So a physicist will tell me now, this was obvious. And okay. Yeah, but now we understood why it was obvious. So it's nice. So I think that's all. I mean, that's all for today. And then tomorrow we'll do the other things I say. Thank you.
Questions?
So you said C114K, but this is just because of the junction. Outside of this junction between the collapsed part and the
yeah.
They're just the
yeah.
Perfect.
Absolutely, yeah. They are actually analytic, right? Because it's constant mean curvature and zero mean curvature. So they're amazing. Yeah.
Someone else? Okay. If not, we go to lunch. Oh, we thank Francesco again.
Thank you.
Welcome back. So we resume this afternoon with Francesca Tripaldi. And thank you.
Thank you. Okay, so basically, I have a general plan for today where I'm going to give you the official construction of a subcomplex that we're going to need. Well, we're going to need. That's what is available at the moment. So there was a choice between giving you a very good idea of the intuition behind the construction or giving you the direct computations of an explicit examples. And I decided to give you an explicit computation. So you will get the construction. I will give you a vague idea of the intuition behind it. Okay. Right. Just the disclaimer. Okay, so yesterday we saw that given a Carnot group G, so you have Carnot group means it's stratifiable, and I am considering the homogeneous structure given by the stratification. So I'm considering with the stratification. And I'm putting a sub-Riemannian structure, metric structure, Riemannian structure. So I have my GDCC metric space, which means that if I consider the Rham complex, this admits, so we saw the explicit expression of D as the sum from D0 plus D1, blah, 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 plus DS, where S is the nilpotency step. And it's also the last layer. So these subspaces are usually called layers of this stratification. So it's exactly the same S. Okay, so this means that, as I told you yesterday, this creates a lot of problems because the increasing weight, so this is usually, I see this as just an increasing weight given by the homogeneous structure, coincides with the differential order of the operator, and it creates problems. Okay. Right. So the crucial problem here is that there are different differential orders, but this, as I said, can be linked to the difference in weight. So for example, just to give you an idea, in the angle group, if I look at so the way I picture this, it's not standard, again, I'm sorry. The way I picture this, if I go down, I'm listing forms with with the weight increasing going down and the degree increasing going right. So if I have the degree, so the weight is P equals to 1, P equals to 2, P equals to 3, P equals to 4, I'm going to have K equals to 1 is theta 1, theta 2. Then I have theta 3, then I have theta 4, then I have 0 and 0, 0. For K equals to 2, I'm going to have 0, 1, 2 forms of weight 1. And then I'm going to have 1, 2 form of weight 2. 2 forms of weight, 3. These are the most difficult computations when you do 1 plus 2. So then I'm going to have 1, 4, 2, 4, 1, 2, 3, 4, 5. And then I'm going to have P equals to 5, which is 3 and 4. Because 2 plus 3 is equal to 5. So the idea is that if I picture this in this way, I have that the difference in weight, so picture this, by an arrow going with slope +1 - 1, this is going to be my D1. So the difference in weight, so it's between a 1 form of weight 1 and a 2 form of weight 2, the difference in weight is 1. Then I'm going to have a difference in weight equals to 2, equals to 3. And it doesn't look like I'm going to have a difference. So it could be 0, right? This will be 0, but nothing tells me except for when I go and compute it explicitly. So I'm going to have a lot of arrows from each one of the 1 forms. So I'm going to have a lot of arrows from 1 forms of weight 1, 2, and 3. Okay, so this is the idea. So I have a splitting of many weights, and this is what is happening. Okay, right. So the idea is that if I manage to remove as many forms as possible without leaving out any information, it's better. Okay, so if I reduce the amount of weights, I reduce the amount of differential orders. Okay, this is the idea. So I am trying to figure out a way to remove as many weights, as many forms, let's say, as possible, in the sense that I don't want to just reduce the amount, I want to reduce the amount of weights as possible without losing info. And by losing info, I mean, what do you compute when you have a complex is the cohomology. So I need to keep computing the Rham cohomology. I want to compute the same cohomology as the Rham complex, okay? So this is the aim of the game. So basically what you start doing is look in the literature, what are the choices available, okay? So there are actually many choices because you have a lot of structure. And the idea is that the fact that the Rham complex is a bigraded complex gives you, this is a bigraded complex. This gives you a lot of structure to play with. So you have a lot of possibilities. So what am I saying here? So I said I could collect K-forms based on the weight. So this is exactly the K-forms of weight P. But I can also collect them as a filtration. So I can collect all the K-forms of weight at least P. Okay? So this is all the alphas of degree. So the degree is K, and the weight of alpha is at least P. So in the angle example, I'm going to do just one forms. So I would have omega 1 greater than or equal than 0. This is all the one forms. I would have all the one forms of weight at least 1. That's, again, all the one forms. Now, all the one forms of weight at least 2, this leaves out the theta 1 and theta 2. So I'm going to have the span, the C infinity G of theta 2, 3, sorry, and theta 4. And then I'm going to have 1 greater than or equal than 3, which leaves out theta 3. So this is just theta 4. And then after 4, I'm done. I don't have anything else. So what I see here is basically, and also it's very intuitive. So if I take the forms of fixed degree, so those that have weight at least P is a bigger space than the forms of weight at least P plus 1. Okay? But this is not going to go on forever. At some point, I have a finite amount of weights. So at some point, this will end into 0. Right? So I cannot have anything. So the idea is that I cannot have any form of weight greater than the volume form. That's nothing. Okay, bigger than the volume form. So this is called a finite decreasing. That's okay. Let's okay. In the literature, you see this as a decreasing filtration of finite depth. So it's just, and I have this on the space of smooth forms, okay? Then I know, so as I said, D is D0 plus D1 plus D2 plus DS. So if I start from a form of weight P, then D alpha is a linear combination of K plus 1 forms of weight at least P. So it's not going to be exactly P because I don't know about the action in general, but I might have a part which is the D0. So this would be the D0 of alpha plus the D1 of alpha plus DS of alpha. This is a K plus 1 form of weight P. This is a K+1 form of weight P+1, and so on, right? So this is an element in this space that I defined. So anything here in the linear combination has weight at least P. Okay? So this means that I have a decrease in filtration of finite depth for which the differential is stable. So omega k greater than or equal than P is still a subspace of omega k+1 greater than or equal than P. Okay, this is a lot of structure. And okay, this is so if you have something like this, there's a lot of algebraic tools that you can use, okay? So there are very algebraic tools, like, I'm going to use a bad word, spectral sequences. Now, if you've never seen spectral sequences, we're not going to see these, okay? But the idea behind a spectral sequence is that you want to compute the cohomology of a complex. So for example, in this case, I want to compute the cohomology of, well, I want to compute the cohomology of Rn. Okay, it's not that deep, but basically I want to compute some cohomology, and I want to do it with this structure, which means that I'm going to compute the bigger cohomology by steps. Now, it is a bit vague, but basically if I have, so the same way that I said before, so if I have P equals to 1, P equals to 2, P equals to 3, and P equals to 4, for example, I start from theta 1, theta 2. I might have a D0, okay? Then I might have a D1, then I might have a D2, and I will have a D3, right? I end up here, I have, the fact that I have this inclusion means that part of the differential is going to stay horizontal, part of it is going to go down, and it's going to go down even more. So the idea is that I am computing the cohomology of the whole D, so the sum of these 4 elements. I do one step at a time. So I do the cohomology of D0, then I'm going to do the cohomology of D1. It's not really that D1, but we're not opening that box. Basically, I'm doing the cohomology that stays horizontal, then I'm going to do the cohomology that has slope -1, then -2, then -3, on top of each other. This, yes. No. No. Yeah, because I said that it's not the same. But we're not, no. We're gonna see this, no. So, yeah, so it's not exactly this D that you need to compute, but it's gonna be a changed D that is based, yeah, so if you've ever heard, it's the zigzag operators come into place, but yeah. D0 is still a complex, we're going to see this. Also, the DS is going to be a complex, but yeah. Yeah. So this is one way. So why am I interested in looking at spectral sequences? Because this idea creates a lot of complexes, okay? So I have the horizontal one, going to have the slope -1, I'm going to have the slope -2, and so on. So this is a tool that I can use if I so choose to. There is also a tool, so this is less algebraic and more differential geometry. This is borrowed from parabolic geometry. So these are called the BGG sequences. So this is Bernstein, Gelfand, sequences. So the idea is that if I have an element, I have a filtered cochain complex that is stable under D, I'm gonna have, sorry, G, sorry, K plus 1, P, G. I can construct a subcomplex by taking the cohomology of the D, which keeps the weight constant on omega K plus 1 P. So this, you should see it as a quotient, but this is the idea. So if I have a filtered cochain complex, then I can simply compute the cohomology of the stable D, the horizontal. So in this case, it would be the D0. It's more general than this. You compute the cohomology of this. This will create a space, a cochain complex, and there is a way to construct a differential operator connecting the cohomology spaces of these operators. So this is much more general than this Carnot group situation. Then there is a very basic algebraic way. So this is, I'm saying algebraic, I mean, if you've ever seen any operads, this is a very basic tool. I can always split any complex into what is known as a minimal complex and a cyclical complex. Now, this is going to sound very obvious. So if I have CD as a cochain complex, I can simply state that M is going to be the cohomology of this, and then the differential map on M, on the quotients, is going to be the 0 map, okay? Because I'm on the kernel of D. What is left outside, so D acts on that, so it is still a cochain complex, but it is a cyclical. A cyclical just means a cyclical, yeah. So this just means that the cohomology of this is 0 in each degree. So I have any complex, I can compute the cohomology and I can leave out everything else. Then everything else is still a complex with the same D, but is a cyclical. So it carries no information whatsoever. And all the information is in M, because I've already computed the cohomology of D on M. And the map is trivial because I'm in the kernel of D. Okay, this sounds stupid, but it's gonna come handy with the extra structure that we have. So these 3 are some tools, and we leave it like that for the moment. Now, we have extra structure. Yes. Yes. These are quotients. I'm not doing any choice of subspaces. This is all quotients, and it's unique. Yeah. Okay, so basically this is, especially what we're doing for 3 is very nice in the sense that we really do want to separate, so to shave off at least the H part from the Rham complex. So this should be fairly easy to do. And it's fairly easy to do and direct because also we have extra structure coming from the stratification, because we have this decomposition, and we know that this is a complex, which means that d squared is equal to 0. So we collect terms depending on the weight. So we have d, well, I just write it this way for the time being. ds after d0 plus d1 and so on. This is going to be 0, but this means I collect them. So this is d0 squared plus d1 d0 plus d0 d1 plus d2 d0 plus d1 squared plus d0 d2 and so on. And I end at ds squared. Why am I collecting them in this way? Because I know exactly the increasing weight now. So if I start from alpha that has weight p, then d0 squared of alpha is going to have weight p. And then d0 d1 plus d1 d0 of alpha is going to have weight p plus 1. So this is an increase in weight of plus 0. This is plus 1. This is plus 2. And you collect them. And then you're going to end up at twice s, right? So we briefly saw this for 1 forms. It can be generalized, but basically forms, K forms of different weight. Now, if you extend the scalar product in a very nice way, this means that K forms of different weight are orthogonal. Now, it's important that they have the same degree, okay? Because otherwise, I mean, they are orthogonal, but they're different degrees. Orthogonal. But the crucial thing is that they're linearly independent. So it means that each one of the addends is going to be 0. Is it clear for that's the crucial thing. So each one, d0 squared is 0. d1 plus d1 d0 plus d0 d1 is going to be 0. d2 d0 plus d1 squared plus d0 d2 is going to be 0. Is it okay for everyone? So this just means I have d0 squared equals to 0. Also, ds squared is going to be 0. Then I'm going to have d1 d0 plus d0 d1 is equal to ds minus 1 plus ds minus 1 ds equal to 0. So it is kind of symmetric in a weird way. But that's the idea. Each one of the addends that increases the weight by j is going to be 0. And so on. Any questions on this? This is the extra structure that we have. So okay. This is much better than the filtration that we had before, because this gives a lot of structure. So in particular, this tells me that the d0 squared is equal to 0, okay? Now, this is symmetric in the sense that I could start everything from D0 or from DS. But the thing is, DS is differential. D0 is algebraic in our case. Yes. It's not direct. And it's not gonna, no, like not direct like this. We're gonna see how to construct the differential. But basically, at least we have a D0 squared. And we decided to start from that one because it's easier for us to compute and to express this as a space of forms if I want to do the cohomology of this, okay? So the thing is that this is, so each dj is not a complex, but this as a whole, so this, the complex, a complex like this for which D0 squared is equal to 0 and D1 D0 plus D0 D1 is equal to 0 and so on. Exactly what we have. This is called, very exciting, this is a multi-complex. And there are many other tools that you can use, many others, I'd like to, but yeah. There are other tools that you can use if you want, if you have a multi-complex. So, yes. What do you mean? Wait. No.
Yes, exactly.
Okay.
Increasing weight.
Yes.
The example D1 is 0, so this is D1.
Yes. Wait.
Yeah. The increase of the weight.
Yeah.
But if we have the increase of the weight by 2 and 3, then we have
A longer, yes, yes. Yeah, it's as you would expect. I mean, it depends. Maybe you have D0, D1, and D2, and then it's fairly okay. It depends on how many S, how big is the S. Yeah. No, it doesn't go any higher than DS because you don't have anything else. So if you had, yeah. If you have something like this, yeah. Yeah, okay. Like you cannot have anything else. So this means that, yes. So this would be, these are all the terms that you have. So it's D0, D2 plus D1 squared plus D2, D0 plus D2, D2, D1 plus D1, D2, and then you have D2 squared equal to 0. So it closes because it's finite. So this is a nice thing. So what can you say after, so after you unblock the term multi-complex, then there is a very scary place, which is spectral sequences on multi-complexes. So one of the issues, sequences on multi-complexes. So one of the issues that people face when dealing with spectral sequences is actually that the differentials, when you start sloping in a way, are never well defined. Okay. This is one of the big black box problems that you had with spectral sequences. In this case, you do have a formula for, I'm going to refer to them as these DIs, the differentials. Actually, I should use delta I for the differentials of the spectral sequence. So it gives you more information. Two, so the Gelfand doesn't get any easier, it's still the same. But the operads thing, you can actually split C into an acyclical complex and a minimal complex, where this time C, I have D with this D0 plus DS. Now I can split C into, what do I call it, H plus M minimal. And this time H is still acyclical, but M is not the kernel of everything, is the kernel of D0 mod the image of D0. You could do exactly the same with DS because it's a complex, but this is just a notation. And then you come up with a new differential on M that computes the same cohomology as CD. So again, I can split M, H useless. M holds all the information, but this time it's not just I'm taking the cohomology groups that I want to compute. I take another cohomology group, and on top of that, I can create a non-trivial subcomplex, okay? And this is to say that everything we've seen, except for spectral sequences, is a bit vague, but there is a link also with spectral sequences, is the same if you do exactly this on Carnot groups. This is the same as the Rham complex. So you can approach this problem from the algebraic point of view, from the spectral sequence point of view, from the Bernstein-Gelfand point of view. Everything constructs the same, exactly the same subcomplex, which is known as the Rham complex. So this is the notation I'm going to use for the Rham complex. So it is a subcomplex, and it's isomorphic as a subcomplex to this MD that is so well done and standard in operads. It's always a nightmare finding out these things. But basically, so this is to say that, yes, like this Rham complex was defined in the 90s, but it is kind of natural. So it can be constructed, as in it's clear that it would come up. It's natural as a subcomplex to arise. So originally, this was not, so what I'm going to present is not the original Rham complex that you may have seen on the Heisenberg group. So this is a disclaimer for people that have had the great luck of looking at the Rham complex before. Disclaimer: before, on the Heisenberg group, on Heisenberg groups, this Rham complex was defined using omega i's and j's, and these are differential ideals of forms. Why was this defined in this way? Because Hn, we haven't, we have seen with Robert's presentation, but it is a very nice Carnot group in the sense that you have two layers. So I have V1 and V2, but V1, so V1 on Heisenberg groups, V1 behaves like a symplectic manifold, okay? So it's a symplectic R2n, so this is even, where the symplectic form is the D0 of the vertical form in a way. So this is one-dimensional, so you have only one form, tau, I'm going to call it tau, and the D0 tau left invariant, behaves like a symplectic form. And for symplectic Kähler manifolds, there was already a way to construct a subcomplex that was done in the 60s, okay? Very traditional. So basically what was done is to extend exactly the same subcomplex, but to the Heisenberg group, saying, okay, I'm keeping exactly the same subcomplex, which is horizontal up to dimension n. This has dimension 2n plus 1, up to dimension n. And then, yeah. Yes. There was a construction. It's not the Riemann complex, because the Riemann complex is on the Heisenberg group. There was a subcomplex. It was in the 60s. Yes. So it was all horizontal, because it's just V1. Okay. So it's all horizontal. So you keep the same. Yes. So, yes, yeah. So it would be like a space of horizontal forms in all dimensions. So what Riemann did was to take exactly the same complex up to degree n, and then you do the Hodge of that. And by the symmetry of the Heisenberg group, this means that it's just the same horizontal forms, wedge tau. So it behaves too well, okay? So it was just an extension of this, because the I's and the J's are very much linked to this symplectic form. And the scary second order capital D is just based on the Lefschetz map. So it is a basic idea from Kähler geometry, okay? The problem is that this sort of construction cannot be generalized to Carnot groups of step higher than 2. So this, bad. No, we don't like that. Okay. But this was the initial point. So it wasn't actually what I've told you all along. It is a completely different one, based on non-commutative geometry, but not nilpotent. It was not the nilpotent case. So then it was actually done in the 70s, exactly the same construction with the omega I and J's from Russians in Norway. Okay, so it was kind of there. It was a very natural thing to do, to play around with. But it wasn't good enough, okay? So now we're going to see the more general way. So the way that kind of reflects what I said here for the acyclical kind of subcomplex, and then the good subcomplex that we're interested in. What time is it? Okay. Right. Hopefully we get something done. Right. Okay. So basically the idea, I used exactly the same notation. The intuition is I'm going to have the cohomology of D0 on one hand, and it's the good subcomplex, and then the bad subcomplex is going to be H, and it's outside of the cohomology. Now, as we've seen, so the D0 coincides with the D, the exterior differential, restricted to left invariant forms. So this is exactly omega LG D0. So this, again, this is the Chevalier-Eilenberg complex, okay? This is a complex. So if you just take the space of left invariant forms, or the space of covectors in a Lie algebra, you don't have a multi-complex, you just have the D0, okay? And this is a subcomplex, and I really wanted to do this because I think it's nice. It's the Jacobi identity, because I spent time doing it, so I like to use it. So the Jacobi identity is the reason why d0 squared is equal to 0. Okay, so if you have a one form theta, which is lambda 1 g, so it's a one covector, and I do d squared of theta. So I start from a one form, so this is a 1 plus 1 plus 1, so it's a 3 form. It should be the 3 form 0. And so I evaluate this on x, y, and z. So this is like saying I have d of d theta applied on x, y, and z. I have my formula for the algebraic part, which states that I'm going to have minus d theta applied on bracket xy with z plus d theta. You're going to have to believe me with the signs. I mean, you can compute them, but it's not that fun. X, Z, Y minus d theta, that is y, z, x. So this is just the differential of the two form d theta applied on that. So this, now I can use the definition of the differential on the one form. So this is just minus theta on the bracket between x, y, and z, minus theta on the bracket between the bracket of x and z with y, plus, theta on the bracket of y, z, and x. So this is simply theta on x, y, z. Is this okay? Yes, because then I want y, z, and x plus, and I invert z and x. And this magically, this is the Jacobi identity. So this is 0. This is, so Lie algebra, and I have a complex. Basically, that's the idea. Okay, so we're ready to define our spaces. So unfortunately, I'm gonna need an adjoint. I have a D0. I have a differential D0, differential algebraic differential D0. I'm gonna have to define the adjoint of D0, the formal adjoint, the transpose. So I did have a scalar product on G. So this means that for any alpha and beta in, I'm not going to count the degree, I don't really care. D0 alpha scalar product with beta, this is defined as alpha delta 0 beta. So delta goes from k plus 1 to k. And I have a nice formula. So the sign should be correct, but it's always a nightmare. N is the dimension of the Lie algebra. K, I'm applying delta 0 on k forms. So this should be the correct sign. This is applied on k forms. So it does, this is the Hodge star that we saw, one of the many stars that we saw. Okay, why do we need this? Because we're going to define F. So remember that the subcomplex we like is E. So this is the complex we don't like. So F0 is defined as the image of D0 plus the image of delta 0. This is just a bunch of forms, okay? Yes. N plus 1 of G, yes. So, nice, D0. So is this closed under D0? So is this a complex? So this is going to be D0 on the image of D0 plus the image of delta 0. So the image of D0 means that this is something like a D0 alpha. So if you do D0 on D0, it's going to be 0. So this is simply D0 on the image of delta 0. So this is an element in the image of D0. So it's an element in F0. D0 stays in F0. Also, a nice thing, the image of delta 0 is the orthogonal complement of the kernel of D0. Right? People that do analysis more than me. This is correct. And we like this. Now, the question is it a cyclic as we wanted in a way? So you can simply check. So I have F0 intersected with the kernel of D0. So if the image, so basically I'm going to have the image of D0 intersected with the orthogonal complement of the kernel of D0 intersected with the kernel of D0, right? So for sure, sorry, this is a plus. For sure, so the second add-in is going to give me the empty set. So this is simply the image of D0. Because it's a complex, the image of D0 is included, is a subspace of the kernel of D0, right? This comes from the fact that D0 squared is equal to 0, which implies that the image of D0 is included in the kernel of D0. So the kernel is the image of D0. And then if I look at the image of D0, then this is simply the image of D0. Sorry, this is the image. So if I do the cohomology of this, this is always going to be 0. This is what I mean by it's a cyclic. Yeah? So no information in F0. So we look at the orthogonal complement. Now, because we want a subcomplex now, we need to have a subspace. So E0 is defined as simply the orthogonal complement of F0. So this is the image of D0 plus the image of delta 0 complemented, which is the intersection of the complements. So this was the orthogonal complement of the kernel of D0 orthogonal complement. So this is the image of D0 orthogonal complement intersected with the kernel of D0. But it's also the same as the kernel of delta 0 intersected with the image, with the kernel of D0. Why am I writing it in these two ways? This one, I see this as the cohomology of D0. So this is isomorphic to what is just, they're all equal, but basically this makes me think of the kernel of D0 mod the image of D0. Right? No? It's isomorphic, it's not a subspace. But it's just a way to imagine it. So this is the cohomology of D0. This one, I see this and I look at it and go, oh, this actually reminds me of something else. So this reminds me of a Laplacian, right? Sure. It reminds me of this sort of Laplacian. And then the kernel of this Laplacian, well, this is actually the kernel. This is self-adjoint, and you have, I guess you have to prove it, but basically this Laplacian carries a Hodge decomposition. So I can see this as a Lie algebra cohomology, because this is the Lie algebra cohomology, the blue thing. I can think of this as harmonic representatives. So this is harmonic representative. Okay, same space, exactly the same space. Right. Now, one good thing about the Hodge decomposition idea is that any subspace, right, so this is still left invariant. Okay, so any lambda k and lambda k plus 1 g star, this I can represent this in terms of the image of D0 plus the kernel of the Laplacian and then the image of delta 0. And then I'm going to have also the image of D0 plus the kernel of box 0 and then the image of delta 0. Okay, so why on earth would I be writing it this way? So D0 is a linear algebraic operator that acts as an isomorphism between the image of delta 0 and the image of D0. So D0 goes in this way. D0 goes that way. I guess you have to believe me, but yeah, it's a linear map. It's a linear map onto the image is going to be an isomorphism. I can invert it. So there is a correspondence between D0 and D0 inverse. So I'm always able to compare completely the image of delta 0 on K forms and the image of delta 0 on K forms and the image of D0 on lambda K plus 1 forms. So those are the same. So they are isomorphic at each degree. This is good because then I have a partial inverse. Also, this is maybe you have to prove, but I don't know. I reached a point where everything is a bit too obvious for me. So I guess you have to prove that the image of delta 0 is the same as the image of D0 inverse. But basically, just point out, the action is not really the same of delta 0 and D0 inverse, but the images are the same space, okay? Right. So far, I've constructed an algebraic Laplacian, a subspace E0 that carries the cohomology of D0 at the moment. I have D0 inverse, so I can construct an orthogonal projection onto E0, which is the kernel of box 0, or this the algebra cohomology thing. Okay. And this, I define this, well, you can see that it is the identity minus D0, D0 inverse minus D0 inverse D0. So basically what I'm doing when I do, so for example, D0, D0 inverse is going to be the identity only on the image of D0 inverse, or the image. This is the projection on the image of delta 0. And then D0 inverse D0 is going to be the projection on the image of D0. I have a Hodge decomposition of sorts. So everything else is going to be the kernel of box 0. Okay? So I removed the parts that I don't like. So this is a projection. I mean, you just compute pi 0 squared is equal to pi 0. I'm not going to do it. It's a projection, and it's an orthogonal projection, and you're projecting onto E0. Okay? So we do like this. Now, the interesting thing is that now we've only worked with left invariant, but all the smooth forms are actually just function onto left invariant. So this can be generalized and extended. This construction of E0 can be generalized as C infinity G E0. I didn't touch any S. So it's just the C infinity G module over E0. And this is the space of Riemann forms. Yay. And I'm going to call it E0 anyway. So it's just a way to say, why did I choose D0 and not DS? Because it's much easier, because E0 now can be expressed as a C infinity G module over something that has constant coefficient. So it's not going to be too horrible. Like it's not, I don't have to actually compute the derivative of the S order, and then I do the cohomology of this. It's just a D0. It's going to be an algebraic operator, and it's fine. It's good enough, okay? It's better than the DS cohomology. Right. So now we need to construct the capital D operator. So we did say that we had C equals to H plus M. So H is bad, is my F0 bad, and M is E0 good. But now we need to construct the capital D, which is for us DC, which is a differential operator that stays, that makes E0 into a complex that will compute the Rham cohomology. So now we need to define the Riemann differential, or this capital D differential. Right. As I said before, there's not going to be an intuition on why on earth I would want to look at these operators. If we had ages, we would actually look at this in terms of spectral sequences. We're not. So I'm just giving you the operators to look at. They satisfy all the properties that we need, and these are good. And these will define the Riemann differential. Right. So the crucial thing is that we need to show that the operators are well defined and that they compute the cohomology that we want. Right, so we do need two things. We need that the D0 is an algebraic operator that preserves the weight, keeps the weight constant. And D minus D0 strictly increases the weight. So it's a differential linear operator that strictly increases the weight. Why do I need this? Because I have two lemmas that I'm going to use. Lemma 1 says that if T is a linear operator acting on omega star G by strictly increasing the weight, then T is nilpotent, which means that there exists an n0 such that T to the n0 is 0. Why? Because I have a finite amount of weight. So if I'm going to increase the weight, it will stop. It will end up at 0. Good for everyone? Yeah? And I'm going to use this to find inverses of operators. I'm going to use this for lemma 2. That says that if I have A0, a linear algebraic operator that preserves the weight, and I have B, which is a linear differential operator that strictly increases the weight, then A, defined as A0 minus B, is invertible, and its inverse has the form A inverse being A0 inverse times the sum between 0 and 0 minus 1, B A0 inverse J, but also depending on how you decide to expand this thing, and 0 minus 1, B AJ inverse, A0 inverse J, A0 inverse. Okay. So this is actually just Neumann series. So if I have, the proof is simple. So I have A0 minus B. This, I think this proves the first equality. So this is the identity minus B A0 inverse A0. Then B A0 inverse strictly increases the weight. B increases the weight, A0 doesn't do anything. So the identity minus BA inverse is invertible, and it has the form sum between 0 and 0 minus 1, B A0 inverse to the J. And then, yeah. So then if you do A0 on the other hand, you get the other formula. But this is just to say that as long as I have an nilpotent group, so I can do these sort of things because the number of weights ends, okay? So increasing the weight is a good thing. And so we have two operators, D0 and D minus D0. So the B will involve D minus D0. So we're going to construct this hellish operator. Right, so we have lemma A, because I decided to change Now we're going to actually look at operators. So this is defined as minus D0 inverse D minus D0. A. With the first two were completely general. This is now to construct what we want. So D minus D0 increases the weight. D0 so doesn't. So D0 inverse doesn't. So this means that B is nilpotent. And the identity minus B is invertible by lemma 1 and 2 altogether. And then I can construct this pi. Pi is right now is magic. I'm sorry. The identity minus B inverse D0 inverse D plus D I minus B inverse D0 inverse. So at the moment, we know that it's well defined because I minus B is invertible. You have to prove that it's a projection. Pi is a projection. And it projects onto the space F. There is a reason why we call it F, which is the space image of D0 inverse plus the image of D0 inverse along E, which is the kernel of D0 inverse intersected with the kernel of D0 inverse D. Orthogonal complement of the first one. I call this E not E0, even though they carry the same information. This is a subcomplex, but it is a subcomplex with the exterior derivative D. I love saying this part because it just makes sense. Right. So if you look at this and you try to no, E0 star is the Riemann complex. But this is another complex, and it is a complex that kind of mimics what we were doing with F0 and E0, because I'm splitting omega G into F and E. And they're both of them are complexes, but they're complexes with the exterior derivative. So you can prove that if you have an element in E and you do the differential, you end up in E, and same for F. It is horrible. Yes. So it may look easier because I have the same differential, but actually the space of forms is horrible. Okay. However, so basically, okay, so I'm going to list just a lot of informations here. So I have that ED is a complex that carries the same cohomology as omega GD. And you see this because of the way I defined this projection pi. Now, pi E, so this is the projection not onto F. This was the projection onto F. So I do the opposite. So this is the identity minus pi. So this is the identity minus, how did I write this? I minus the inverse D0 inverse D minus D I minus B inverse D0 inverse. Okay? It's just the other. You have it actually, it's long, but it's easy, unfortunately. It's just it's kind of confusing on, like, if you look at this the way I presented it, just with Rham's explanations, there's no reason why this should work. And the reason is that in order to compute the same cohomology with the D, you need a map, a homotopy map. Okay, so this role is played by this zero inverse. Okay, this just tells you that this pi e will compute the same cohomology. So this is pi e and pi e. But actually, I don't really like E as a subspace because it's a mess to compute. So I'm going to rely on the fact that pi e pi 0 pi e is equal to pi e, and pi 0 pi e pi 0 is equal to pi 0, which just means that E and E0 are in bijection. So they're carrying the same information. So this just means that pi 0 pi e is the identity on E0, and likewise pi e pi 0 is the identity on E. So it just means I can rely on the E complex to compute the cohomology of E, which is the cohomology of omega G. Okay, so I'm projecting pi E, I'm doing D, and then I'm project down on pi 0. So the DC is actually this. So I rely on E, horrible forms, but I can reach E via pi E. And then once I'm there, I can just use the differential, and that will compute the same cohomology, and then I project down onto E0. Importantly, d pi E does not end up at E0, so I really need to project down. Again, in the way you find, so if you Google and you find literature on the Rham complex, this is what you find, okay? It is not intuitive whatsoever why I would have to do this. But basically, what are you saying? You're saying I need to find just some maps that make sure that I'm computing the same cohomology, okay? And then if you look at it hard enough, you actually can rely on other algebraic structure that actually give you the real intuition. So the algebra, so the fact, so what I'm trying to say is that I need, so the big difference between the Rham complex and, for example, the operads complex is that the Rham complex is a subcomplex. I need specific representatives. I need a subspace of forms. So I need a choice for D0 inverse. I want a specific, very explicit expression for both the pi e, the d, and the pi 0. Okay, whereas if I do just the algebraic operatic thing, they're quotients, I have an existence thing, I'm happy with just a very intuitive idea behind this construction of D. Okay. The problem is that when you just look at the construction without the intuition behind it, it's horrible. It's just you get lost. Yeah. It's the same. It does, yeah. So all the BGG, I mean, it's just yeah, I mean, you don't do much with it. Yeah. So the BGG, so it is, what I'm trying to say is that it is a very natural way to come up with a subcomplex in this way, like separating the good part and the bad part. The problem with the Riemann complex is that because I need a subspace, I need to come up with these pi e maps. Okay, so if you're just given the pi e maps, you don't really understand where they're coming from. But one thing I can tell before finishing is that this I minus B inverse, so it looks horrible, and it is horrible, but it is better, the expression for the pi 0 d pi e, if I start from E0 star. Why? So pi e here, so one big reason why this looks so odd is that I need these two addends. So I need both I minus B inverse D0 inverse D and D I minus B inverse D0 inverse, because pi e needs to be a projection. But actually, if you start from E0, I'm on the kernel of D0 and the kernel of delta 0, okay? Which means that this pink term cancels out. It will always be 0. So the idea is that if you actually know what you're looking for without having to rely on these projections, because you need to apply these theorems from algebraic topology to say that, oh yes, it computes the same cohomology. Actually, this one you don't need. This is extra information that nobody is interested in that. So actually, the pi e simply becomes, I have the identity minus a D0 inverse D plus a D0 inverse D minus D0, D0 inverse D minus D0 inverse D minus D0 squared D0 inverse D, and so on. But we know that this ends at some point because I'm increasing the weight. So I don't have the second addend, which is actually what throws out any semblance of intuition. Actually, you don't need it. So again, this pi e actually is easier than you think. So, I mean, looking at it like this, it's not that nice, but it's much nicer than the other one. So I have this way. So the way I see this, so you start from an element in E0. Now we're going to see, tomorrow we're going to see this applied to angle. But basically you start from a function, sorry, for a form on the kernel of box 0. So this, you have to apply pi e of alpha. This is alpha plus elements of weight higher is with an higher, and derivatives of alpha. I have pi e alpha, so I have alpha, it generates alpha plus some stuff extra. Then I have to do d of pi e of this. And then I get an element which is unfortunately not in E0, it's in E. And so this, just because I have this correspondence between the elements in E and the elements in E0, I can project it down. So I just have an element again in the kernel of box 0. Okay, so this is the idea. So the way Rham decided to explain it is to rely on this E subspace, because it's easier to show that E computes the same de Rham cohomology as the one that we want. But it is, yeah. I mean, pi E is a hell of a lot of information if you start from omega. So basically, the whole expression for pi E was needed to show that ED computes the same cohomology as omega D. Sorry, I'm looking at this. The pi E in its full form was used to show that ED computes the same cohomology as the de Rham cohomology. But actually, the actual form, the simplified form that you can define on E0 actually reflects much better what is done in the other construction. So in the BGG construction, or the spectral sequence construction, or the operad construction. We're going to see tomorrow, we're going to see that it's not as bad as you think it is. Or maybe it's worse than you think it is. I don't know. But yeah, thank you.
Questions? Comments? Valentino.
So two curiosities. So in a sense, E star is a kind of intermediate step between the standard Rham and the Rham complex. And that maybe you can use in some cases is better to work with that with respect to kind of.
If you feel like it, yeah, why not?
It's okay.
I don't.
Because that's a curiosity.
I would, but no, there are people. So basically, if you don't want to work exactly on kernel D0, yeah, then yes, why not? So it is just, so E0 is just a choice that you can make for E, more or less.
Also, E star
but it's
depends.
an easier one.
Yeah. Also, E star depends on the scalar product you fix, like E0 star. Also, this is sensitive of your choice of the scalar product.
What is E0 star?
E0 star, the Rham complex.
Yeah.
Yeah. So in that case, you choose the scalar product. No, it's very sensitive. You have delta.
To construct
that is
exactly.
Yeah. The same is for E star. You also need the scalar.
Yes, because you have to rely on the D0 inverse anyway. Yeah.
The second curiosity is at some point you before the previous the next slide. Sorry. Yeah. So I didn't understand. No. Slightly before. Yeah. There. No, a little bit. Yes. In the definition of PI. So I didn't really understand when you remove this part and you say, so this is part of the operator.
This is the whole operator.
Operator, yeah.
It's just when you apply it to E0.
It disappears, that part, when you apply on the, okay.
Because it's on the forms that are in the kernel of D0 inverse.
Okay.
So if you have as a first thing D0 inverse, that's going to be 0.
Okay. Thank you.
Other questions? If not, we thank Francesca again. Okay, so now it is my pleasure to introduce Reinaldo Resende, who will talk about regularity of area minimizing currents.
So hi, hello everyone. So first of all, thank the organizers for inviting me. So I'll be talking about regularity of area minimizing currents. I will add some words to this title as we move because we need like some more information. And so the plan is the following. I will try to give some motivation and basics on currents. A lot of the concepts that I use here already appeared in other talks, so it will be just like, you know, reorganizing stuff so it makes sense for us. Then, I mean, we'll introduce some more stuff that has appeared before, and then we are going to start talking about regularity. And I will talk very shortly about the codimension one case, but the focus of the talk will be understanding how things work and how they differ from the codimension one case in higher codimensions. So I'll try to pace myself to not go very fast, and I'll try to keep it as simple as possible, but please ask questions. I'll be happy to answer. Okay. So the problem that we are interested in studying is the Plateau problem, which is stated like follows. Given a curve in R3, find the least area surface which spans gamma. So this has already appeared in Francesco's talk. He's talking about this a lot. And I mean, the motivation for the problem is some like experiments ran by Plateau in the past. And okay, after Francesco's course, I should add the word dry here, so it should be dry Plateau problem. But okay, yeah, I'm taking the course too. So, so everything that I'll be talking about is the dry Plateau problem. There is no wetted region or anything like Francesco is doing. Okay. Amazing. So the motivation is the same. We take a wireframe, we dip it into a bucket of soapy water, and then we pull it out, and then we have the soap film that forms. And I mean, approximately this guy will have like nice properties like mean curvature equal to 0 and things like that. And we want to study properties of these guys that we will call minimizers in a while. And we know, like, as Francesco has presented, that these guys might have singularities depending on the type of wireframe that we are dipping in the bucket. Okay. So let's reformulate the problem in a mathematical way and more generally, and then let's talk about some problems that appear. And again, this problem they have appeared before in Francesco's talk, but let's remind ourselves of like what is the overall situation that we are trying to deal with. Okay, so we have a smooth boundary, gamma, here. It's a -1 dimensional manifold, so you can think about a curve in R3. So the Plateau problem reads as finding the infimum, like showing that there is an infimum when we try to infimize the area of smooth surfaces that spans this boundary gamma. Okay, so we have a fixed wireframe, and then we are taking smooth surfaces that attaches to this wireframe, and then we are trying to find the one that has least area, right? Okay, of course. So the first thing, if we want to solve this problem, we are trying to prove that this is actually a minimum instead of infimum, right? But then we already run into problems, which are what would be like the first strategy to follow. Prove that this is finite first, and then show that take a minimizing sequence, so something that converges to the infimum, and show that the convergence, the limit set also belongs to the same space, and then we have our minimizer, right? But that doesn't work in the space that we are setting up stuff here because we are dealing with smooth manifolds. So if we take, and we know that if we take a sequence of smooth manifolds, there is no reason for the limit to be smooth, right? I mean, we can take a sequence of catenoids like this, and this is going to converge to a singular object, right? So this guy here, okay, this is not like an example of like anything here, but if we were to do an argument like this, now we are in a new space of objects, and then we are not really solving the problem that we are stating here because this guy is not smooth. Okay? Is that okay? Okay, good. So great. So this motivates us to try to find new notions of manifolds and new spaces of manifolds in which we can actually solve our problem using arguments like the one that I just described. So we are trying to find a new class of generalized manifolds which enjoys good convergence properties, and then we can try to run an argument like this and show that we actually have a solution to our problem. Okay? So same framework as in Francesco's mini course. And usually, okay, so I should add a fourth point here too after Francesco's course, but usually in GMT, we have these three more standard ways to approach this problem of generalizing the space of manifolds. The first one is working with Cacciopoli sets. The second one is working with currents, and then we have varifolds. So what are the differences between these three things? First, Cacciopoli sets, they are a theory that works in codimension one. Okay, so it's a nice theory. It does solve the problem using an argument like that, but it's only suitable for codimension one. Okay, so what is the next question? Okay, how do we generalize this for higher codimensions? So currents will be the answer. We will talk about currents a lot, so for now it's just a name, but that's the main thing about the in the talk. And then we also have the theory of varifolds, which is more general than these currents. But the reason that we are going to work with currents is that we have a very nice boundary operator in this space. Okay, so again, as Francesco has been talking a lot in his course, finding the right way to span a boundary is a big deal, right? He has like all these homotopic spanning conditions. So this is a big deal. It's not something easy to do. And actually in the space of varifolds, it's not clear how to define a boundary. So this is why we usually work with currents, because there we have a good boundary operator, and then we can derive stronger properties. Okay. So these are the overall differences between these three spaces. Okay. Amazing. So I have to, now we are going to try to understand what these currents are. So I have to set up some notation, and then we can define the space of the currents that we are going to be interested in. So this notation is just differential geometry. So there is nothing really new here. It's just a notation that I'm going to use. So if we take an m-dimensional oriented manifold of class C1, we can define the linear functional associated to this guy just by integrating differential forms over this oriented manifold, differential geometry, right? There's nothing new here. I'm just associating a linear functional to a smooth manifold. Okay, amazing. So with this, we can already define the these currents, and then we are going to define the space of currents that we are going to actually work in. So we call an integer rectifiable M current. So this is a linear functional defined by that's written in this form. So this okay, so let's forget about rectifiable sets just for a second, and let's say that these guys are smooth just for a second. Okay, so we are taking these linear functionals and we are summing them up where these MIs can be different, right? So I mean, for instance, we can think about like two planes crossing, right? M1 and M2, right? And then we are taking the integral over each of them, and then we are summing it up. So these guys are already singular, even if we replace rectifiable by smooth, right? By this example. And on the top of it, we can also have a repetition. So, I mean, we can take, like, for instance, M1 to be equal to M3, right? And this is what we call multiplicity, because we are going to be integrating one time over M2 and two times over M1. So in the integral, we are going to see two times the integral over M1, one time the integral over M2, right? Okay, so these guys, they are already singular, even if we think about these MIs as oriented, smooth C1 manifolds. But actually, everything that we are going to do work if we replace smooth by rectifiable sets. So take like all the examples of rectifiable sets that like Robert has talked about, for instance. Sorry. Oh, sorry. We can have repetition too here, right? So we can have yeah, I will say like two words about this. So if we take any example of rectifiable sets, we can use the same idea as in there, and then we are going to have this multiplicity. And yes, as Valentino mentioned, this is not actually the definition of integer rectifiable currents. It is slightly different in the textbooks, but I didn't want to give you the definition because it's horrible, and there are some components in the definition that we are not going to care about at all for this talk, so I don't want to make things more complex for this talk, right? So this is an instance of integer rectifiable currents, but actually the definition is slightly more general than this, which is where the density comes. We have the density there in the definition. Okay, but for the purpose of this talk, this already conveys all the problems that we have in the regularity theory. Okay, good, amazing. So these are the integer rectifiable currents, and okay, this guy is a linear functional, right? So when we are working with general currents that are just like linear functionals, we can, via the Riesz representation theorem, we can associate these guys to measures, to a set, which is the support of this measure. In this case, our measure that we would denote like this, so the total variation of t, will be just the sum of the Hausdorff measures of each of these MIs intersected with whichever set we are plugging here. Okay? So we are counting multiplicity. So look at this example again. If we take a Borel set somewhere in here, we are taking the total variation will be the Hausdorff measure, but then we are summing this guy once, and then we are summing this guy twice, right? So you're already seeing some multiplicity there. Okay? Good? How are you feeling? Okay, amazing. Good, so this is our setting. Again, this is a nice setting. It's slightly more general than that actually, but this is good for the talk. Okay, so okay, this is the same definition, just to keep it here so we remind ourselves what we are talking about. And now we are going to define the boundary operator in this space of currents. Okay, so this is, I started the talk by saying that this space is good because we have a nice boundary operator, so let's define it. And the definition is very intuitive. So let's start motivating the definition by using smooth geometry, right? So if we have a C1 smooth manifold, right, M, we can, we have Stokes' theorem. So for any M minus one dimensional form, so if we take the exterior derivative, this is a M form, right? And this is an M manifold. So we are good here, right? This is defined as this quantity, the integral of the whatever form we have here over M. And then Stokes tells us that this is the same as integrating over the boundary of this guy, which we are assuming to be smooth, the M form, the M minus one form itself, right? And this is, again, by definition, the linear functional induced by the boundary, right? Just by the definitions that we gave. Okay? So this is for smooth manifolds, right? We don't have like, we only have Stokes. Stokes, we can apply this for simplices and stuff, but this is smooth manifolds. So for currents, we use the equality here with the extremes of this chain of equalities, right? So we take a current, which is a linear functional, so we replace this guy, which is induced by a C1 manifold, by the current that we are working with, right? So we have the current in the exterior derivative, the same term that we have here, and then we have the boundary on this side over the form itself, right? And these will be our definition of boundary. Okay? And of course, this is a M minus one form, so this guy will be M minus one current, so the dimensions are correct. Any questions? No? We good? Okay. So now, amazing. Now we have our notion of boundaries. So let's try to understand how this notion differs like from classical differential geometry, just to see what we will be working with. So let's see two examples. And you guys are going to tell me that I'm crazy about these pictures because they will appear like 10,000 times in this talk. But it's because they illustrate very well like the boundary type, the type of boundary points that we are going to see at the end. Okay, so let's say that our current is the current used by sigma 1 and sigma 2 here, these two smooth surfaces. And then, I mean, each of them is separately, there are smooth surfaces touching at this boundary here, right? So if we apply Stokes for each of them, we are going to get that the boundary of these currents 2 times the boundary gamma, right? Nothing to do here, just do differential geometry there. Okay, so we have this kind of multiplicity business that I was mentioning in the blackboard appearing also on the boundary. And this is going to be a big deal for us at the end. Okay. And also we have other kind of boundaries here. This is just like to introduce this picture because it's going to be important. But for instance, if we take this chi plus to be the smaller disk, and then we take chi minus to be the bigger disk, but the whole disk, right? So we have that when we integrate, we are going to see this guy here also as a boundary, right? And this example just to highlight, this guy gamma, it's kind of the interior of S, right? Because it's inside the disk, but it also behaves as a boundary, right? So in a functional analytic way, gamma, this inner piece of gamma is a boundary, and in a set theoretic way, it's an interior for our current. So we have these things being mixed up when we are talking about boundary of currents. Okay. Questions so far? No? Okay. So these are the currents that we are going to care about. These are the integral currents, and they are currents that are such that both the current itself and the boundary are of this form. So they are both nice enough. Go ahead. Sorry? Oh, that's a good question. I don't know, actually. That's a very good question. I will search this up. I don't know. I don't know. Okay. Yeah. Okay. Yeah, it's the that makes sense. Yeah. Yeah, here's the answer. Thank you. Okay, so we are going to work with these integral currents, and they are currents such that the guy itself and also the boundary are written in this nice way. Okay. Because again, I mean, the boundary is just a linear functional, right? So it's not necessarily written like that. So we have to assume it. Okay. Good. So, okay, I introduced what these currents are. So why do we care about them? First, nice boundary operator. This answers one of the questions, but okay, I mean, we define a boundary, so I mean, why do we care about defining a boundary for something? Because we want to solve the Plateau problem. That's our goal. So we have to show that this space actually fits and it solves the problem that we are trying to study. And this was a theorem by Federer and Fleming. I'm going to be very quick in this slide because this is not like the goal, but Federer and Fleming, they proved that a space of integral currents equipped with some certain topology, that's not going to be important for us today, has good compactness properties. So meaning that if we take sequences of integral currents with nice bounds, then we converge up to subsequences to an integral current, okay? So in particular, as I was mentioning, the Plateau problem always admits at least one solution because we can run that argument with minimizing sequences. Okay, so this space is nice for us because it actually solves our problem. We can actually find solutions to our problem in this space, and these solutions are what we call area minimizing currents. Okay, good. Okay, so but now again, we are trying to study the Plateau problem, and we have these new solutions, but now they look weird. They might be singular, so we have like less properties, and we have all these difficulties that we have to deal with now. We have densities, we have boundary multiplicity, as I showed in the green example, and also the other example. And they might have singularities because like we are dealing with rectifiable sets, so there might be a lot of singularities, right? So we have to deal with these things now. So, I mean, the holy grail, so the thing that we would love to have is that currents, they have this behavior, but we would like to say that if we add area minimality, so we add the assumption that this guy is a solution to a problem, then they are entirely smooth, and then we are solving the Plateau problem in the classical sense in differential geometry, right? But as we all know now, like, these are not going to be regular. Because I mean, even in the experiments and stuff, these things are not regular. And I'm going to show examples of singular area minimizing current. Okay. So since we are not going to be able to show classical existence for the Plateau problem, meaning smooth solutions, we want to understand how regular these guys are. So like, is the singular set small? Is the singular set big? How much we can say about the regular part of this current so we can do classical differential geometry on it. Okay. So that's the thing that's what like regularity theory concerns about, and that's what we are going to be to see from now on. Okay. Oh, sorry. Questions so far? Are we good for this motivation part? So it resembles a lot of the things that Francesco was saying because it's kind of like studying the same kind of problem, but in different settings. Okay. Great. So now I need to introduce these more technical things, but they are crucial. Without them, I won't be able to to say anything about the regularity theory. But they are more like measure theory concepts, just to recall, and so we are all on the same page. Okay, so T will be our integral current, right? And Q will always be a natural number for the talk. So the density of an integral current is just the density of measures. There is nothing new here. So we denote the density of an integral current, of course, when the limit exists at some point x as the limit, as the density of the measure associated with the current, which we are using the notation here, the total variation, right? So it's just density of measures. But for our guys that look like these, our measure is just the Hausdorff measure, right? Nothing new, everything that we see in measure theory courses, right? Great, so let's see again these examples, and again, this is going to play a big role. This is why I'm stressing both of them. So if we take again T to be sigma 1 plus sigma 2, so the sum of the two green manifolds, of course, the linear function was induced by them, then if we try to compute the density at this point P, so what we see, it's the Hausdorff measure at each of these guys. This is a boundary point for each of them. So sigma 1 will contribute with 1/2, and sigma 2 will contribute with 1/2. Since the current sums everything, this will be 1, right? And this is already a problem in some sense, because this is not what we expect from a boundary point, right? Boundary points are supposed to, the density for nice things are 1 if we are on the manifold, 1/2 if we are on the boundary, and 0 if we are outside the manifold. And here we are already seeing boundary points behaving like interior points in this measure theoretic sense. Okay. And this is even more interesting. If we take S to be the same as before, so the big disk and the small disk, and we take the point P, so we have density 1 coming from the big disk and density 1/2 coming from the small disk. So the density is 3/2, right? So the density at boundary points can be integers, can be bigger than integers, can be weird, right? And of course, the density at the point Q is equal to 1/2, because this is a honest to God boundary point, right? And this is also another weird behavior, because on the same boundary, we have different types of boundary points. So we have a point that is actually what we expect from a boundary point, and we have a point that is all messed up, right? So on the same boundary, we have things that behave completely different. And of course, this is an example, but when we are dealing with currents in our general setting, we don't know how to differentiate P and Q, right? So all these things will be mixed up, and the density actually is a big problem for us. Okay, so last thing that I have to introduce are the tangent cones, which, we just take rescalings of our current. So let's say that our current T is this black line, and we want to define this TPR, so it's just the rescaling. We look at the ball radius R, we blow it up to the ball radius 1, and then we see how the behavior of the current is there, and we denote this guy by TPR, right? And the blow up is when we take R to 0. So these guys converges, and for this specific current, we might have two different types of blow-ups depending on the sequence that you choose of R's here. So the blow-up depends on the sequence that you choose. Okay. What do I want? Okay, yeah. So these are the rescalings. Then we have the blow-ups, and for our area minimizing current, so for the things that we are gonna care about, we can show, and this is a consequence of something that we call monotonicity formula. we can show that the blowups, they are always cones. Okay? Because a priori, there is no reason to have like any kind of properties of the blowups. We are blowing up rectifiable sets, right? I mean, we know that blowing up rectifiable sets can be a terrible thing to do. But if our currents are minimizing, if it's a solution to our variational problem, then we can say stuff about the blowup. Then the blowup has to be a cone. Okay. Great. So same thing written here. This EA shouldn't be here. Okay, and then we are going to talk about flat points, and these guys are the ones that we are going to that are going to be important for us. A flat point is a point for which the blow up. So when we blow up the current, we know that the limit is going to be a cone, and we are going to call the point flat if the limit is supported in an M plane. So it's not just a cone, it has to be actually a plane. Okay? Is that okay? TP. Yeah, I'm being a little bit sloppy here because in this definition, I'm kind of embedding uniqueness of the blowup, but I'm using TP for the blowup. Okay. So this is an example of a point that is not flat, right? Because if we blow up the current around the point P, we are going to see two half planes. Because this is a smooth manifold, and this is a smooth manifold, right? We are going to see two half planes. This is not flat, right? Two half planes, it's not supported in an M plane. Okay. And in this case, for instance, if we blow up at any of these points, then any like P or Q, it's going to be a flat point, right? This guy is going to blow up to a half plane, and at this guy, we are going to blow up to a whole plane with multiplicities and stuff, but it's going to be supported in a plane. Right, so here we have two examples of flat point, and here we have an example of a point that is not flat. Okay. Questions about flat points? Go ahead. Oh, I was missing a sum? There is a sum over I. Thank you. Yeah. I'm sure they're missing a sum here. Thank you. Yeah, should be the same sum as in here. Sorry. Thank you. More questions or comments? Okay. Chi plus is the whole disk, big disk, but the whole thing, right? Including the small disk. And chi minus is chi plus is the small disk, and chi minus is the big disk, the whole big disk, including the small disk. It's gamma. Gamma is the union of the two circles. Yeah. Yeah, gamma is the union of the two circles. Good? Okay. Yeah. It is exactly, yeah. It's important. Everything on current, and I will talk more about this too, we have an orientation always, and that plays a big role too. Someone, yeah. Yeah. Okay. Amazing. So let's start talking about codimension one, and I chose to talk about it here because that's exactly where I want to say stuff about these flat points. Okay. So we are concerned about the boundary, we are concerned about regularity of these currents. And let's try to understand first what happens in the codimension one case, which is kind of like the well-known case by now. And we have these things that we call epsilon regularity theorems. So we are in codimension one now, so n is equal to 1, right? So this is only true in n equal to 1. If T is area minimizing, then we have the theorem that says that flat points, they are actually regular. Okay, so around flat points, if you have a current and you have a point where you blow up to a plane, then around that point, your current is a smooth surface, is a smooth manifold, right? So they are completely regular. But if you are around a flat point, and more also important, codimension one, right? So this was originally identified by De Giorgi, and for interior points, and then Allard proved for some type of boundary points, and then Harden-Simon generalized for more general type of boundary points. I'm going to talk about this type of boundary points, but in higher codimensions. Okay, so okay, so yeah, I want to say like a few words of how the proof goes. I mean, this is going to be very superficial, but just to have an idea, because the goal is to understand what changes from codimension 1 to higher codimensions. So I need to say as least stuff as I can about the codimension 1 case to be able to talk about the higher codimension case. So we have our current, and we are assuming that we have a point. So I'm going to use here this notation just to make stuff easier. Such that TP is a plane, right? So we have our flat point. P is our flat point there. Okay. So how things usually go? So we have our current here. So that's doing all sorts of weird stuff, right? And we know that around this point P, so let's say point P here, just for sake of the picture, this is the nicest point. We have that we are converging to a plane. The current's blowing up to a plane. So how do we usually do stuff? So first step, we try to approximate our current. So we approximate T by a function that's Lipschitz and defined in this. Of course, I mean, I am identifying currents with the support, like with the sets related to them here. But we approximate the current T by graph of Lipschitz functions. So we are taking a Lipschitz function here that's doing all sorts of stuff. And I'm going to write U instead of the graph just to make the picture less crowded. Okay, so this is usually the first step. We approximate it, and then we use minimality. We use minimality, so T area minimizing implies that we can actually approximate by a harmonic function, right? So this is a lot more structured. So we can approximate T by F harmonic. Okay, so we know that we have a flat point, so the tangent, so we blew up to a plane, we approximate by Lipschitz functions, then we use minimality, so we use the fact that it's a solution to our problem to approximate by better functions, which are, oh, we lost the red chalk, which are actually harmonic, so they are much smoother than the function U, right? And I mean, all these steps are non-trivial, but after approximating by harmonic functions, we can use regularity for harmonic functions. It's like we have like a million tools to use there to show regularity of the current T. Okay, so these are like the main steps of an epsilon regularity theorem. Okay, and it's the same thing for sets of finite perimeters, right? For those who are used to the George's theory or Francesco's book, for instance, it's the kind of technique that the people use to prove regularity. Okay. Now, amazing. This is codimension 1. How do things change in higher codimension, and why am I talking about like these precise steps of the proof? Because all the regularity theory in codimension is based on these epsilon regularity theorems. Everything is like follows from here. But we have super bad news, and bad in quotes, because it gives birth to a beautiful theory, which is the one that I'm going to talk about. That for higher codimensions, so n greater than 1, this fails. We cannot, epsilon regularity theorems, they are not true. We cannot run this kind of procedure. Everything just cracks down, and then we have no tools to use anymore. Okay, and we are going to spend some like few minutes to try to understand why it fails, because this example, it's kind of like I would say the most important, because it encompasses all the difficulties essentially of the higher codimensional setting. Okay, so this is called Federer's example. This is the current F, which is the current induced by this guy. So this is in the complex. This is in C2, right? And I'm taking Z squared equal to W cubed, right? So two complex numbers, and we have an equation for them. Okay? So this is the set that we are caring about, and we are taking the current induced by this guy. Okay. So what are the claims? So why is this guy important? First, this guy is area minimizing. So this I'm not going to prove. The proof is not complicated, but it kind of goes sideways to the things that I want to talk about. But we use the theory of calibrations to prove that this guy minimizes area, and this was proved by Federer. But for us, let's just believe that this guy minimizes area because, I mean, the other stuff are more important. Okay. And here is the thing that we care about. 0 is a flat singular point for this guy. And I'm going to justify this a little bit. So singular, I think it's okay, right? I mean, this is a square root, so 0 is singular. We cannot like write this as a smooth manifold around 0. And flat, why is this flat? So why, if we take this current and we blow up around 0, why does this give us a flat point, a plane, right? So, I mean, this is just a simple computation. So if we take 1 over r, so you want to blow up this guy, this is going to give us this equation, right? Just doing like the computations. And when we take r to 0, this is equal to 0. So it's a plane, right? Now, the claim is that the current induced by F, because these are the sets, so I'm taking the current induced by F now, this is converging, this is blowing up to 2 times the current induced by this limiting set. Okay, so I think that the density is okay, seeing how the 2 appears, because we have the 2 branches of the complex root, and they are closing up, right? So we have 2 branches, so they are collapsing, and then we get density 2. Is that okay? So, oh, that's a very hard question because I mean we have to think in R4. There is not much to do. I do have one picture for the boundary that I think that it's very illustrative. So let's hold on a little bit for that part. But yeah, it's a little bit kind of like, it's a little bit hard to visualize these things. And even for the boundary picture, the picture is not like very precise. I'm going to say some stuff, but just to give an intuition. Okay. So do we believe that this is true, that this guy's converging to 2 times the plane? Is that okay? So amazing. So I mean, we have a current now, and this current is area minimizing. 0 is a point here on this part of the current, which is flat because we are converging to 2 times a plane. So it's supported in a plane, and it's singular. So this theorem fails. Counterexample, right? So now we don't have epsilon regularity theorems anymore, so we have nothing to work with. And there is, there is even a bigger problem here. So first thing, it fails. We can have flat singularities. That's the first takeaway here from this example. The second takeaway is, even if we, let's say, we have no hope to prove an epsilon regularity theorem, but do we have hope to at least adapt the strategy to get something from out of it? The final answer is yes, we can, but we have to do a lot of work. And one intuitive reason is our first step is to approximate our currents by functions, right? By a Lipschitz function, then we use minimality to get extra properties. But first we approximate by functions, right? Like, I mean, around these kind of points, there is no way that we can hope to approximate this guy by a classical function, because we have 2 branches, right? It's a complex root, so we have the 2 branches, so no hope to approximate this guy by a classical function in a way that things work, of course. And here's where Almegren has introduced the notion of Q-valued functions, mut-valued functions. So this is a different notion of functions that takes several values, and with these functions we can approximate these guys, and we can run a regularity theory. We have to study what's the harmonic counterpart of these Q-valued functions. So there is a whole theory that has to be developed in order to approach this problem, and things are not so nice as for harmonic functions. But this is the second biggest problem when we go to higher codimensions. Okay? Yeah, you can surely set up the problem. There are different spaces of currents. You know, you have flat chains, you have mod P currents. I mean, I'm aware there are a lot of results for mod P currents about regularity, but I'm not aware if there are results for other spaces of currents. I mean, there are surely results in codimension 1, but in higher codimension, I would say that's more unlikely that there is nothing other than area minimizing in integral and area minimizing mod P. But in codimension, I'm sure that there are more results, but I'm not like very familiar. Good. Okay. Good. So now we have these two problems in higher codimensions. So I'm not going to talk about like these Q-valued functions. This was just so you know that there is a problem here. There is a whole field of research in here too. But I want to show you guys how the theorems look like in higher codimensions, the theorems that we can prove. We are not going to prove them because the proofs are pretty lengthy, but I want to give you like an overview of how things go. Okay, so how are we feeling about the codimension case, about the differences? We good? No questions? Okay. Okay, so let's see how things go in higher codimensions. So now we are going to care about higher codimensions where we don't have epsilon regularity theorems. So first thing, just to be precise, we have our current. We are going to call the interior regular set the set of points where T is written as a smooth manifold. Okay, so completely regular. I'm not even allowing like two things smooth crossing, right? So this guy is not allowed. This is a singular point for us. This is a lot of structure because this is smooth and this is smooth, but this is not regular for us. Okay, so regular, it agrees with one single smooth manifold. So it's a very strong requirement, right? We are trying to go from rectifiability with densities to the guy agreeing with one single smooth manifold, not like with unions of smooth manifolds. So we are jumping from rectifiability directly to just like one smooth manifold. It's stronger than jumping from rectifiability to unions of smooth manifolds. Okay. And the singular set is the complement of the regular set. Every point that is not regular is singular, and this is the notation that we are going to use for the interior. Okay. So the theorem that we have in higher codimensions is that if we have an area minimizing M current in Rm plus n, then the interior singular set has Hausdorff dimension at most n minus 2. Okay, so we cannot rely on epsilon regularity theorems as in codimension 1, but there is a whole theory to show this dimensional bound. So recall that our main goal was we have this new space where we can solve the Plateau problem, right? We would like to solve it in a classical way, so solve with smooth things. We can't because these guys are singular, but we want to understand how smooth they are. And that's the answer. I mean, up to a set of Hausdorff dimension n minus 2, at most n minus 2, our guy is smooth, right? And then we can use differential geometry apart from this set. Okay. And the next question is, can we do better than this? I mean, can we do better than n minus 2? The answer is no. This theorem is sharp, and we are already familiar with the example, right? It's the same example. This is a area minimizing 2 current in R4 if we identify C2 with R4, right? This is a 2 current in R4, and 0 is a singular point because this is a square root. Okay. Again, I'm just hiding the fact that this is area minimizing. Okay. So this is, so the Hausdorff dimension of the singular set is equal to 0, and in this case, m is equal to 2, so we have optimality. Okay, so we can do better than that. That's the optimal result that we have. And okay, the next comment, this is not like, okay, if you're not familiar with these things, ignore my next 3 minutes, please. This is just more for people to know that this theorem is a little bit more general. But if you're not familiar with this, ignore this next theorem. So we are actually able to prove that this same theorem work in abstract Riemannian manifolds of class at least C2 alpha. So the same regularity theorem, if you replace Rm plus n by a smooth manifold of class at least C2 alpha, then you have the same bound for the singular set. Okay, and the reason that we stop here, these guys, they proved this result for Almgren for C5 and the Ledges Spadaro for C3 alpha. We proved for C2 alpha more recently with Stefano. And we stopped here, not because we have to use Nash's isometric embedding theorem to work with these things, because we want to go back to the Euclidean space. But there are also other problems if we try to do this in C2. I mean, if you are interested, we can talk about this, but that's the state of the art for non-Euclidean spaces. Okay, so those who have tuned out, please come back. Now it's going to be important again. Okay, Great. So again, we have the singular set. The singular set is small in this Hausdorff dimensional sense. And then linking to your question, okay, amazing. We are mathematicians, so we want to know more, right? We have the singular set, so we want more information about this guy. How bad is this guy? Because, I mean, for instance, if we have two planes crossing, we have a whole singular line, right? Of a whole line of singularities, right? But the line itself, so the singular set as a set is a line. So it's very regular as a set, right? So can we say something like this for the singular set of an arbitrary area minimizing current? The answer is, okay, it's not going to be so nice, but it's going to be rectifiable. Okay, so this is a set that is of Hausdorff dimension at most n-2. So in the right Hausdorff dimension, this guy is n-2 rectifiable as a set. So even on the singular set, we have information, we have tangent planes n-2 almost everywhere. We have all those things that Robert was talking about for rectifiable sets, even for the singular part. Okay, so we have a bunch of information about these guys. Okay? Questions? You're good? Okay, so, and this was proved by two groups of mathematicians. This was proved like at the same time by them, Camilo, Paul, Anna, and also Brian and Nishan. Okay. Okay, so that's it for the interior. Let's see if I'm not forgetting anything. So now we are going to jump to skip to the boundary. How are you feeling about the codimension one, the interior? Everything okay? Good. Okay, so now the boundary setting. How does that work? So the boundary setting is much more intricate because all those things that I have already mentioned and I will mention again. And so we are going to have different types of boundary points that we care about and that we will want to understand better. So this is the statement. So of like, this is the theorem that we have. And I mean, this is what we are going to discuss for the rest of the talk. So I'm stating the theorem, but we are going to discuss this a lot. So let's say be an area minimizing current that takes the boundary. Like this is a C3 of this is smooth, guys. So the boundary is smooth, and we have a current with a smooth boundary and some multiplicity. I will put the pictures here again to see the examples. So then the boundary regular set is dense in the boundary, right? So the boundary regular set of the current, so the points on the boundary where the current, around that point, the current is smooth surface attaching the boundary. This guy is only dense in the boundary. We don't even have a Hausdorff dimensional estimate. It's just a topological result. Okay, and that's what's going to be most of our discussion from now. So let's try to understand it a little bit better. Before moving on, in codimension one, the result's much better. In codimension one, there are no boundary singularities. So in codimension one, all boundary points are completely regular. Yeah. That's I'm going to talk about this a lot. Yeah. Yeah. There are open problems in this direction. That's going to be like kind of the main thing. And I will construct an example that I mentioned for one of the questions that shows that this is almost the best that we can hope for, but it's not exactly the best that we can hope for. And again, in this is any codimension. In higher codimension, in codimension one, all boundary points are completely regular. There are no boundary singularities. So we are jumping from no boundary singularities to density, right? So it's a big jump, and we are going to see the why they are different. It's regular, yeah. It's a C3 alpha or C infinity manifold. Yeah. So the boundary is regular, and we are trying to study regularity up to the boundary. Yeah. Yeah, and there are interesting open questions depending on the smoothness of gamma. Not smoothness, actually analyticity, but yeah, I will mention things about that too. Okay, so let's give credit where credit is due first. So when the multiplicity here is equal to 1, this was originally proven by Camilo, Guido, Jonas, and Annalisa, that's here, in 2018 for Q equal to 1, so the multiplicity 1 case, okay? And I want to say just one word about, again, about like higher codimension versus codimension one. So we see some of the difficulties appearing. I mean, this is already a very groundbreaking theorem, and there are a lot of complicated stuff that they do there. So there is a big jump from codimension one to higher codimension, but again, there is a big jump when we change the values of Q. And the reason is in codimension one, so let's say that we have an area minimizing current, let's say that it looks like this, okay? Just for like the explanation. And this is in codimension one. So in codimension one. So let's say that our current looks like this. The thing is, in codimension one, we have the two finite perimeter sets, right? So if our current looks like this, we can associate to these guys two finite perimeter sets, right? One guy in here, and let's say that the other one is up here, right? And this is a theorem. It's not like completely trivial, but it's kind of well known. Because in codimension one, we can order stuff, so we know how to say, oh, this point is the height of this point is higher than the height of this point. So we order the heights, and then we can write the finite perimeter sets. And since this is minimizing, we know that each of the pieces separately, they are minimizing too. Because I mean, if this piece is not minimizer, we replace it by the minimizer, and then this new piece with T2, this will be the actual minimizer. So this guy has to be minimizer separately. And then we can use classical theory for finite perimeter sets. So we have epsilon regularity theorems, we have everything to use here. So the point is, if we know regularity theory for when we have only one piece, so when Q is equal to 1, we can jump to any Q in codimension 1 just by a cheap decomposition argument. We decompose, and then we can use the case where Q is equal to 1, right? Just, okay, to be extremely clear, Q is equal to 2 here, right? We are taking this boundary with multiplicity 2. Each one is taking the boundary with the right multiplicity. Okay? So that's not true in higher codimensions, because in higher codimensions, we don't know how to order stuff, right? So this cheap argument doesn't work, and we don't have like a decomposition argument that comes before regularity theory. We have to develop a whole regularity theory to be able to talk about the composition of currents in higher codimensions. Okay, so this is what I've written here. So these arguments due to white, so the argument that I just described, the decomposition of currents in finite perimeter sets in codimension 1. So studying currents in codimension 1, in this sense, is essentially studying finite perimeter sets. And that allows us to always reduce to the case where Q is equal to 1, right? Again, in higher codimensions, this doesn't work. Okay, so jumping from Q equal to 1 to arbitrary Q is not completely trivial, but we were able to prove this too with Stefano first for two-dimensional currents, and more recently with Ian, he's a PhD student in Princeton. We were able to prove this in full generality. So there is open problems regarding the optimality here, but we solved the whole thing now for any regime of Q and M. Okay. Okay, so now let's start answering Valentino's questions. So is this the best that we can say? How does, if not, how does the example look like, right? So the answer is, the result is dimensionally sharp, meaning that we won't have a Hausdorff dimensional estimate. That's not possible. And this is due by this example that was also in the same paper by Camilo, Guido, Jonas, and Annalisa, where they show an example of a two-dimensional current in R4. So the boundary is one-dimensional, right? It's a curve. So it's their example, the curve is infinity. And the dimension of the singular set is actually equal to 1. So it's equal to the Hausdorff dimension of the boundary. So we have equality. There is no hope to get a Hausdorff dimensional bound here. Okay, but there is one thing about their example, which is that the measure of the set is 0. Okay, so this leaves open the question, well, can we show, okay, we have density, but can we show that the measure of the singular set 0. The dimension, no hope. Their example already says that there is no dimensional estimate. But can we show that the measure is actually equal to 0? Open question. We have no idea how to do. And I mean, the techniques that we develop in either of these papers, I mean, there is no reason to believe that any of these techniques will solve this problem. So it's a pretty wide open problem. Okay. Yeah, exactly. So this, yeah, so this, for instance, is, okay, we already talked about codimension, so let's erase codimension here for a second. So this is an example of a boundary with multiplicity 2, right? And if we are hoping to prove some regularity in multiplicity 1, this is the only thing that we want to see, right? This, I mean, we want to prove regularity theorem. So you want things to look like this for some type of boundary points. I will get into this. And we want, in things, we want to look like these if the multiplicity is higher. So the problem is, in here, we expect that our current is written as the graph of a function, right? It's going to be a smooth manifold, so locally we can do this kind of stuff. Here, we don't have this hope. So again, we see the problem where we have to use Q-valued functions instead of single-valued functions, because again, we are in higher codimensions. So, and we don't know how these currents look like. So we might have like several branches, like complex roots and stuff, attaching to the boundary, and then we have no hope to write this guy as a single-valued function. Yeah. And okay, and this is for a specific type of boundary point that I will describe in a second too. Okay. Good. Okay, so so now we are going to try to understand the construction of this example. Okay, so I think it's very elucidative in some sense, and it's a very nice construction. I mean, the proof for this theorem is very lengthy, but the construction of the example is not like so. It's not horrible. It's a very nice construction. So the current, so the final current that we are gonna have is the sum of the disk. So it's this disk here, plus the graph of certain function that we are going to understand. So it's going to be the disk plus the graph of a certain function. And let's try to understand what the function is. Okay, and just one reminder, okay, we are in C cross C, right? So I mean, this is a line, but I mean, I drew these lines as a line, but these are two. So remember that we have weird stuff going on there too. Okay. First thing that we do, and this is, unfortunately, I cannot talk about the proof because time is limited, but Jonas showed the construction of a holomorphic function on the half complex plane, so Rios positive, that extends smoothly up to the boundary. So the boundary of this guy is this line, right, of the half complex plane is this guy. We are saying that this function, I mean, it's holomorphic in the interior and extends smoothly to the boundary. So it extends smoothly to this line. And the set E that's given by, I mean, the line, right, intersected with the point where G is 0. So the 0 level set of G on the line has Hausdorff dimension equal to it. Okay, so this is a complex I mean, this is a construction in complex numbers theory. There is nothing to do with currents, this construction, right? But we use this to construct these examples. Okay, so we have this function that extends smoothly to the boundary, and then we define this set, and this set will have, it's part of the construction that the set will have Hausdorff dimension equal to it. Okay, so what we do is, okay, I mean, this is a holomorphic function, so the singular set is discrete, right? So the singular set will be like something like the green points here. It's discrete, right? And then we can choose a closed smooth curve, gamma in C infinity, that avoids the singular set of this smooth, of this holomorphic function, because the singular set is just discrete. So we can contour it and avoid the singular points with a smooth function, right? Great. Oops, sorry. And then, I mean, we avoid the singular set in the interior, and then when we go to the boundary, we attach here smoothly, and then we include the whole line, and then we detach and continue doing stuff. Okay? Great. So now we set omega to be the region encompassed by this curve, gamma, right? So it's a closed curve. So we take the region inside the curve. And I mean, this construction of the curve, this is in C here. It's on the base, right? And now we can take the graph of our function over this region. Sorry. So we have the region omega here, and now we are going to take the graph of this function g over the region omega that we defined, right? So we are going to take the graph of this function over the region omega, and this guy that should be a g here. There is no u. Sorry, this should be a g. This guy is the one that we plug here in the definition of the current, right? So first of all, we defined omega, this set omega to be the interior of this curve, right? This curve is smooth, right? So, I mean, the whole contour of this guy is completely smooth. It's infinity, right? Because we are taking the image of a holomorphic function over a curve that does not see any singular point of the holomorphic curve. So the contour in orange here is a completely smooth curve, and the rest of the boundary of T is the circle, because it's the boundary of the disk. So it's the circle union with the orange thing. So it's a completely smooth boundary. It's an infinity boundary, right? And the problem is, and the reason that this picture is not like very precise is because, like, again, we have to imagine this in R2, and I mean, we can't, but you have to imagine that this guy is like twisting around the axis and doing kind of weird stuff to attach to the boundary here. Okay, so what is the thing with this example? The thing is, whenever G is 0, so remember that E is the 0 level set of G on the line, right? Whenever G is 0, G is touching the disk, because the disk is like Z equal to 0, right? And then this cannot be a regular point for the current, because you have a disk and you have something that it's not a disk attaching to the boundary, right? So you have like two pieces, and this is not regular. So, and this occurs at any point on the 0 level set of G, right? But I mean, the construction, Jonas construction gives a 0 level set that has Hausdorff dimension 1. So the singular set of the current has Hausdorff dimension 1 because it coincides with the 0 level set of G on this boundary here, on this line. Okay, so and as I mentioned when I talked about the open problem, this set that Jonas constructs, so set E, which ends up to be the singular set of the current, this has measure 0. And I mean, you can actually see that this construction cannot be modified by using this type of complex functions to give something with a positive measure. So, I mean, this example tells the most that it can tell us, and that's it. No, that's just because of the techniques that are used. You might be able to find different techniques to construct a worse example, but then you would be solving the open question that I present. I mean, I'm not saying that it's not possible. It's just like in the direction of the open question. But this example cannot be modified because the construction is pretty much optimal. No, I mean, okay, there are two things. I'm using the holomorphic function. I mean, gamma is the curve. So yeah, gamma is the curve. The boundary of the current is the image, is the graph of the function over the curve. No, but okay, but then how do you show that if you have like this minimal surface and the disk, this will be area minimizing? Because you need to know that this configuration is area minimizing. And because in this way, we can show that this is area minimizing by using calibrations. Exactly, yes. So yes, I agree with you, but if we use different stuff, how do we prove that it's area minimizing? And for this, we can use calibrations. It's essentially the same argument that Federer is used to prove minimality of subvarieties. Okay. Good. So this is the construction of the example. And just to remind ourselves, so this is telling us that this is almost optimal, but it's not optimal because we still have like this open question. And this would be interesting because then we can, when we integrate over the boundary, we can ignore the singular set, essentially. So this would give us a lot of information as well. Okay, but yeah, we don't know that, and I believe that our techniques in the way that we do, I mean, the techniques in this for newspaper also don't like apply to solve this problem in a very straightforward way. Okay, so amazing. So now, okay, so this is, I mean, this is a theorem, right? I mean, we have density of the regular set, okay, but density, well, I mean, for measure theory, we cannot do like very much with density, right? So we would like to say more about the singular set. And so let's try to understand if we have extra properties for the boundary, if we can say something more about this regular set. Okay, so we are going to try to understand how things behave with respect to the density, right? So we have densities, points of density like Q/2, Q/2+1. So we have all the types of density, and then we will try to understand now if we can say more in the range of the densities here. Okay, so so for these, I'm going to define two types of boundary points, and these are the things that we call one-sided points. And these points are the points where we have density Q/2. So first thing about the density, we have a lower bound for the density by something that we call monotono density formula. So the density is always bigger or equal than the multiplicity of the boundary over 2. So it's always bigger or equal than this number. So the possible densities on the boundary is always to the right of Q/2. So a point will be one-sided if the density is the multiplicity of the boundary over 2, which is the case that we have here. Remember that the multiplicity of the boundary is 2, right? And the density is what? So 2/2, right? And we have these other type of points that we call two-sided points, because around this point P, the density is 3/2, right? Remember that we did this computation, the density is 3/2. So the density is the multiplicity of the boundary, which is 1, so 1/2 plus 1, 3/2, right? And this is what we call two-sided points. And I mean, in these pictures, it's kind of clear why we call it these two-sided points, because we have current on the both sides of the point. Okay, I mean, this is hierarchical dimension, so sides is like not a very precise word to use, but that's how we think about these things. It's a regular, it is smooth. It is smooth. The boundaries is smooth. The boundaries is smooth, and we want to understand if the current is smooth up to the boundary. So the boundary really looks like this. The current is the one that we don't know if it's so regular like in the pictures. Make sense? Okay. So we have these two type of boundary points, and again, we have the example. Like, so I mean, if we don't split into types of boundary points, we cannot say much about the boundary regular set, right? Or other than density. So let's try to understand how these things, why these things are important. So first thing, we proved that if you have an area minimizing current with the boundary like Q gamma, multiplicity Q, so any two-sided point is a regular point. Okay, so any two-sided point is actually regular. So being two-sided is a very strong thing because we can actually prove regularity. We proved something slightly more general than this, but that's fine. These appeared before also in Guido, Camilo, Guido, Jonas, and Annalisa's paper, but in a different formulation, and also in my paper with Stefano. But this was for different types of. Our two-sided points are more general than the ones that appeared there, just for reference. Okay, so two-sided points are fine. They are nice. They are good. We know how to work with them, but they have this strong condition that we have a whole open neighborhood of points that look like this. Okay, good. And now, so two-sided points are not a problem. So the problem has to be these one-sided points and other types of points. Okay. So if we are with density close to Q/2 plus 1, so we have a two-sided point, Q/2 plus 2, so other types of two-sided points, we are good. We have regularity. We are good with these points. So for these regimes, for density in these regimes, we can prove regularity. So we can get rid of these now because we already understand it. Okay, this was a previous version of the talk, so ignore like this red line. Now we are going to try to understand the one-sided points, so points where the density is equal to Q/2. Okay. So first thing I want to say is, okay, I mean, this is a condition on the density. can we relate this condition on the density with other conditions that are more familiar to us to be able to apply results and stuff? The answer is yes. We showed that if you have like a smooth boundary, as always, and the boundary is either a closed and connected surface, so you have like these two topological properties, it's closed and it's connected, so let's skip item 2 just for a second. So if it's closed and connected, then all points on the boundary are one-sided. So we don't see two-sided points. So if we have these two topological properties, well, amazing. We only have to care about these one-sided points. So this is another interesting reason to study the one-sided points, because a lot of boundaries are closed and connected, right? And also there is another condition that implies the same thing, which is this convex barrier condition. We call convex barrier, but the condition says that the boundary, so gamma, is contained in the boundary of a C2 uniformly convex domain. So like the boundary lies in the on a sphere, for instance, right? So it's in the boundary of the ball, which is a C2 uniformly convex domain. So if you know this, if you know that your boundary is on a sphere, for instance, then all points are one-sided. Okay, good. So these two conditions, which are kind of like more familiar to us, they show that all points are one-sided. So great. So let's try to understand a little bit better these one-sided points. So I mean, we can have like regularity things to apply. And okay, there are like a few things that I want to say, but that's about like the last thing that I will say. So as always, we have an area minimizing current, a smooth boundary. There are no conditions on the boundary here. Okay, it's just smooth. Then first thing, the set of one-sided singular points is completely empty if Q is equal to 1. So we have multiplicity 1. So we expect to see the second picture there, the picture on the right-hand side, just one manifold attaching for one-sided points, or when the dimension of the current is 2. And so Q is equal to 1, it was proved by Allard, and M is equal to 2 was proved by Camilo, Stefan, and Simon. Okay, so two-dimensional currents or boundary multiplicity 1, then there are no one-sided singular points. One-sided, right? So density, in this case, the density is 1/2 because Q is equal to 1. So if you know that the density is 1/2, or if you know one of these two properties, you don't have singular points in this setting. Okay. Well, question, can we generalize this? Can we say more? And then there is this new example by Ian. He put this out this year, that there is a 3-dimensional current with multiplicity 2, which has a one-sided flat singular point. So the boundary of like this example is also infinity, and 0 is a one-sided point. So the points that we are caring about now, but it's flat. So the current converges to a half plane, and it's singular. Okay. So two-sided points. So the points that look like points that the current behaves like around P here, these are regular. But if we have one-sided points, this is not the only kind of pictures that we are going to see. We are going to see singular stuff here too. Okay, so this is what Ian's example shows. And then we are able to show that the set of one-sided singular points has Hausdorff dimension at most n minus 3. And this gives optimality of, Ian's example gives optimality of this, because when m is equal to 3, we have that the Hausdorff dimension is 0, and we have one singular point in this example. So the Hausdorff dimension of the point 0. So this theorem is optimal by Ian's example. And also we were able to show that as for the interior, but the singular set, the one-sided singular set, boundary singular set, is rectifiable in the right dimension. Okay, so essentially almost, for one-sided points, all questions are answered. There are not much to say for all dimensions. For two-sided points, we have regularity. Now, we have the interaction between one-sided and two-sided points that allows for the kind of examples that we constructed that might have like very complicated singular sets. Okay, So again, I mean, why do we care? I mean, this is important. Why do we care about these one-sided points? Because I mean, we have nice conditions to check that the whole boundary is formed by one-sided points. So if you know that your boundary is closed and connected, or you have like that it's contained on a sphere, for instance, you can apply this theorem, and then you have a Hausdorff dimensional estimate, and then you can do much more stuff. So these are easy to check. So if you don't care and you don't want to know what a one-sided singular, what a one-sided point is, but you have this, then you can already apply this directly. You don't even know to know. You don't even need to know what a one-sided point is. Okay. Okay. Let me see. Okay, I'm not going to. Okay, I was planning to construct Gia's example, but that's going to take more than 10 minutes. So any questions? No. Let me just say another thing. There are some conditions to show that we only have two-sided points on the boundary too, but I mean these are topological conditions too. But there are other conditions, but I thought it was like too much for the talk. But we also have an understanding of topological conditions implying that we only have like two-sided points, for instance. Then we have regularity. But I think that one-sided points are the ones that we expect more on the boundary, right? Because I mean, they really behave like a boundary point. Okay, so I think that I will stop here. That's it.
Thank you, Reinaldo. So, are there questions? Yes.
Thank you for the nice talk. Is it possible to have any kind of idea why the boundary regularity is so tough? There are only these cases. You know, in principle, one might think that no, you can consider the boundary as the current that you minimize. So some vague ideas like that, but of course you can. But
yeah, sure. Okay, so I would say that the easiest way to see this, comparing with PDEs, for instance, in codimension one, we have like maximum principles for PDEs, right? So I mean, what is the thing with regularity theory? We approximate by.
Sorry, I reformulated the question. Even in high codimension, you have the regularity theorem that the singular set has dimension n-2. You don't have this for the boundary regularity.
For the interior, we have the singular set. Yes, and for the boundary.
For the boundary, you don't have
okay.
this. Yeah.
So the thing is,
so why is it difficult to have this? Yeah.
It's essentially a problem with. At the core of the thing, it's a problem with the unique continuation, because all these results, they are unique continuation type of results. And the thing is, Almegren can prove that like these unique continuations result, I mean, with modifications, they kind of work for these Q-valued functions. But we have no hope to expect that a unique continuation works for the boundary in hierarchical dimension, because it doesn't work even for harmonic functions, right? You have like examples of two-dimensional, harmonic functions from a ball in R3 that is zero. The function and the normal derivative on the boundary, they are zero in a set, and you don't have that the function is zero. So unique continuation fails even for harmonic functions in a classical sense, for classical harmonic functions. So I mean, there are other reasons, of course, but like an overall, like kind of like the core reason is unique continuation is a problem even at the level of harmonic functions on the boundary.
Thank you.
Other questions?
Thank you. Just to know how bad the picture is, so you say that in codimension 1, there is regularity. When we pass to codimension superior, we lose that, but are there results saying that we lose that often, or they are somehow a rare set of currents on which we lose that?
That we lose the regularity of the current?
In codimension superior than 1, you have problems that do not appear in
Yes.
codimension 1.
Yes.
So do we know if among the currents that you are looking at, these problematic ones are often or rare, or?
Okay, I understand your question. So there has been a lot of like progress in this direction. This is what they call generic regularity. So the thing is, okay, you have a boundary data, right? So for that boundary data, these are the results that we have. But if the question that you can ask is, well, if I modify a little bit my boundary data, like in some topology, I put like some perturbation of the boundary data, can I find an actual like smooth minimizer? There, like for Q equals 1, the answer is yes. For Q greater than 1, we don't know. But there are more results in this direction. But that the state of the art is like we have answers for Q equal to 1, we don't have answers for Q greater than 1. But that's what we call like generic irregularity.
Okay. Someone else? Okay. If not, we thank again Reinaldo